Welcome, everybody. It should be Monday, March the 31st for you. Before we get started with the main content, just as an introduction, this is the agenda for today. We have the Easter break coming up, so I wanted to give like a bit of guidelines for what's coming up next. Our agenda looks as follows. First, I will say a couple of words about assignment number 3, then we'll look at news articles, and then the course recording gets started. First of all, in terms of assignment 3, by now the instructions and the information with regards to this assignment should be posted on Toledo. The reason why we get started with this before the Easter break is so that during the Easter break you can already make sure that your installation, your Spark installation is correct, and you can already get started by gathering articles. So you will connect to a streaming textual data source. You will have to gather the data from there yourself. And you can already get started by doing that. So that's why it's handy to have these 2 weeks available so that you can make sure that you have sufficient data available. The goal of the assignment 3 is not to be spectacularly good in terms of accuracy or something like that, but you do need at least to have some data in order to train your model on, or to build your models on, or to execute a project on. Setting up Spark can also be a little bit tricky, depending on, or I should say, depending on whether you're on Windows or on Mac, there might be different issues that can pop up. So the zip file that you can download from Toledo, it has clear instructions posted, but the zip file also includes a recording both for Mac and Windows to show you how to set things up. In case of issues, there is also an FAQ, a frequently asked questions section, available as well. So normally, hopefully, things should go relatively smoothly. Also, with regards to the course recording, the content hasn't changed that much. This is kind of the data science tools session, so you can go over that. It's kind of like an overview, and that might be already pretty familiar for many of you, and also based on things that we saw before. Now, especially the last part of this course recording, where we talk about versioning and package managers and containerization and also deployment issues, those are pretty important. The content of last year's recording hence doesn't match 100% with the slide stack that you have. And I wanted to pay particular attention that some extra slides have been added this year with regards to newer Python package managers, mainly UV and Pixie.sh. In short, to kind of recap on this, UV is kind of the modern replacement that you should utilize if you would be using pip already, or pip plus venv, or pip plus virtual env, or you would be using something like Poetry, which last year was like the newest and most modern kit on the block. Nowadays, you should utilize UV to do that. I've completely switched to that. It's enormously fast. It's faster than pip. It's very clean, and especially for Mac and Linux users, it also supports Windows, but especially for Mac and Linux users, this is a fantastic tool. Now, there's also something called Pixie.sh, and this one tries to be a replacement for the Conda package manager and virtual environment manager. Now, Conda has had a couple of alternatives that are compatible to it before. There, for instance, we've had Mamba, and just as Conda has micro Conda, you also have micro Mamba. And the difference with the non-micro ones is that this doesn't install like a default environment with already a bunch of packages in it. There you can just get started from scratch. So in the past, there was already something like Mamba that you can look up. It's mentioned on the slides. That was already better and faster than Conda, but fully compatible with the Conda repository. Now, that being said, Pixie.sh is their kind of the new thing, because what people find a little bit annoying with things such as Conda is if you look at where your environments live and the definition of your environment, that it's somewhere installed on your system, but not really local to like a project directory. And that's already something that UV did as well, is this notion of there is this PyProject TOML file, or TOML files in general, which is like a configuration file describing what your environment needs, and also putting the virtual environment in your project directory itself. But typically that's not something that you would put on GitHub. You just put a description there, and then if you need another machine to set up an environment, it can set it up based on that description. And so also Pixie is taking a very similar approach, but rather than only being compatible with the PyPy package repository like pip does or that UV does, Pixie wants to be compatible with the Conda repository, with the reason being that Conda offers more than just Python packages. It basically offers a whole bunch of compiled binaries, which especially for Windows users, is if you ever want to install something like PyTorch with GPU support, or Conda, or you need to install the OpenJDK, for instance, it's more than just Python packages. So especially for Windows users, it's quite helpful, and that's the main reason why we have been using Anaconda. Annoying, however, is, like I said, that these environments live like somewhere on your machine and are not local to a specific directory. So these managers, they step away from this idea of, oh, first you should run like conda activate. That's totally separate from whichever folder you're in. Here, the environment lives in the folder, and if you're in the right folder, that basically then you know, given the TOML file, which environment you're in. So the two clean newer tools, UV and pixie.sh, you should try taking a look at them, and as a replacement for pip, as a replacement for venv. I mean, both use venv under the hood, but they kind of are the best of breed. And it seems like every year the Python world comes out with a new package manager / virtual environment manager. That's the state of the situation right now. But this is what I basically wanted to highlight. The reason why I'm yapping about this is not just because I'm pretty enthusiastic about these tools, which I am. So I'm using Pixie on my Windows machines and I'm using UV on all my Mac machines. I've kicked out Conda completely. But the reason is also because the instructions for this year for assignment number 3 use pixie.sh, right? So if you follow the instructions, if you follow the videos, you will be kind of getting a taste of what that looks like yourself as well. That being said, if you're like, yeah, but I have already installed Anaconda, or I'm already using Conda, I know how that works, I don't want to switch, you don't have to, right? And the instructions, we use pixie add and pixie init. If you're a Conda user, you should just be able to create a new environment and use Conda install and install the same packages as what we are installing with Pixie, because they're using the same repository anyway, right? So that will work. Now, that being said, for the love of God, if you're already a Conda user and you have been just using the default base environment and dumping all of your packages in there, that's of course not the way how you should use Conda either, right? So the whole idea is that the reason why we have these different environments is exactly because we want to have something clean, local to projects that we work on. And with Conda, sometimes it's a little bit easy to miss, because if you install the Anaconda installer, it sets up a base environment and you have scikit-learn in there already. So you're like, okay, I can just work with that. But that's the whole idea of these package managers. So hopefully, if you go through assignment number 3, if you have a chance, use Pixie. It works on Windows, Linux, Mac, so that's not an issue. And you will get a feel of how clean that looks and how smooth that it is to utilize. So that's something that I wanted to highlight as well with regards to both assignment 3 and the course recording. That being said, we will get started with in the news, afterwards the course recording, and hope you have a nice Easter break, and definitely take a look at setting up assignment number 3 during that time. Okay, welcome to the In the News session. Like always, there has been so much stuff happening in the space of generative AI that it's basically impossible to put it all in the news section. But okay, here goes. I think the key thing to start with is OpenAI has introduced 4o with image generation. This is the page. Yeah, I mean, they couldn't be far off after Gemini did it with their experimental model. Now also OpenAI has released something. According to Sam, their GPUs are melting. They're pretty proud of what they've done, rightly so. The first thing that they put in, yeah, I mean, if you're a bit familiar with AI, this blows you away. The consistency of the text here is fantastic. You might have seen, or if you're following this a little bit as well, you might have seen as well, like everybody who was like working with Photoshop or a designer, I mean, people are worried. We spoke about diffusion models. They are combining some sort of diffusion model with an autoregressive transformer, like seems to be the style these days, which regresses from top to bottom. But they have a bunch of tricks under the hood. It's again a little bit of a pity that, yeah, the examples are fantastic, but seems like the open source community will have some catching up to do to kind of reverse engineer what the things are that they did here. It's yeah, pretty crazy. If I don't know what your Twitter page looks like, but if it looks like my page, you have been overwhelmed with Ghiblification, meaning take an image and convert it to Studio Ghibli style, and then you give that to Kling or Runway and you make a video out of that. And you get all these sorts of memes like this. Yeah, this has been the world basically. But it has other examples as well, like you hand draw an image and it basically makes the cartoon for you. I mean, this is crazy. If we compare this with what I was telling about a year ago, the speed at which this has gone is yeah, simply fantastic. There are so many examples that I could show about this, and it's not just Ghiblification, it's all sort of styles. The consistency of this model is great. There are people making movie posters about this. There are people making advertisements about this and so on. Yeah, a lot of memeing going on, obviously, right? So I do need to be a little bit careful about what I show here. But Yeah, a crazy world that we live in. If you would look for a technical report, there isn't much out there yet, right? So we're kind of, or the community is hoping that there will be some technical report going on. The same thing, or it seems to be that engineers talk to each other because, like I said, the Gemini Exp model that we saw a couple of weeks ago, Flash native image generation, they seem to be using similar aspects. I already mentioned this, I think, even a week ago, that the consistency of this is so good that they must have been cooking up something new. This was March 12th, for God's sake. So now it's March, end of March. And yeah, these companies are doing similar things. I hope that the open source community can catch up with this. But that's not all that happened. Again, there are like a couple of companies, like Qwen has released, so another large kind of lineage in this week has been again a release of more language models. Qwen has been releasing newer, smarter, lighter. So you see how the push is going forward, models become smaller, and there is this double shift towards making them smaller and making them better. This is Qwen 2.5 with 32 billion parameters. A little bit large, but I mean runnable nowadays and outperforming other models in the same space. Qwen has always been known to be a very good coding model and helpful for coding tasks and to integrate that, to run that locally and integrate that in some sort of autocomplete plugin in your VS Code or something like that. So also nice to see that this is still going on as well. Then this is another paper, and we'll see something that's maybe a bit related, but this comes from Google Research. They present an article where they propose to use a large language model to decipher language processing in the human brain. So their study shows that neural activity, so they monitor the brain for neural activity, and that this seems to, and this is pretty crazy, it aligns linearly with the internal contextual embeddings of speech and language within large language models as they process conversations. Why is this crazy? Because we basically have constructed, I'm wary to say another type of intelligence. I'm not that overblown on this, but we've constructed something that at least is very good at pretending to be intelligent. Maybe so are we, but through two different means. One is trained with backpropagation through an enormous amount of data following post-training attempts. So a completely different system than what biology has cooked up. So it's a bit remarkable that if you then start comparing like speech production in an LLM on the one hand and speech comprehension in a human on the other hand, that there is like a very close match in this embedding space, in this token space that's going on. Very interesting that there is still like research being done on this. So they have transformer speech to text and they map that with speech areas in the human brain. Very interesting stuff. Reminds me a bit of things that Neuralink is also working on, but definitely check this one out. This is another article called AI will change the world, but not in the way you think. Just a blog post, basically, but I liked it because this person is basically not arguing against LLMs, but he's arguing against the way how we humans have been using them, that we use an LLM to convert a series of bullet points, this basically into a complete email. And then on the other side, there is a human going, well, here's my email. Can you please convert this again to a summary of bullet points? And yeah, that's inefficient. And he's basically arguing for like business speak 2.0, where we all start to become better at recognizing AI fluff. And in a way we are. And just go back to talking in bullet points or making emails in bullet points and be very to the point. And he kind of envisions or predicts that that's going to be what happens next. I thought that was a pretty fun read as well. DeepSeek has come out with not R2, but with v3.1. Not so much focusing on reasoning capabilities. But again, a new model that is extremely cheap, extremely easy to run, and again, seems to outperform others in the same, let's say, class, including Claude Sonnet 3.7, or coming very close, depending on the task that's been given. Some task is basically completely overshoots everyone else. Very interesting, completely free to use. You can locally download these models. So DeepSeek has been doing very interesting stuff there as well. This I thought was pretty cool as well. This is something that Meta Labs has been working on. Of course, Meta still heavily invested into virtual reality and so on. There has also been a lot of models being released that in the past weeks that convert images to 3D, and also this area is rapidly evolving, incredibly fast. But here we have a model that can take a single picture and basically generates a 3D scene from that. It's not the first model. These are called world generative models or world building models. So it's not the first time that we saw that. Last year, I remember there were already early examples of this. What is different is that, again, the quality looks way better than what we had a year ago. The next step obviously is going to, again, it will be a combination of these different models. Now this is a fixed viewpoint where you can rotate the camera around. Of course, you want to walk in this world, right? And there have been early attempts for this as well. That's not what these authors are showing, where you can take a few steps forward and you have like an image model kind of hallucinate kind of the new position, give that to the other model, a 3D viewpoint again. But nevertheless, the consistency that's being shown here is from a single image. I mean, we live in a crazy world where we in a way still want to travel, but on the other hand we might not need to, especially if you want to enter fantasy worlds like this. So this is again very nice work. I'm a bit of an enthusiast in terms of these kind of asset models and 3D models and mesh models and so on. So I don't want to overload you with that, but I think this is just amazing. My kid self would have been out of the world for this kind of stuff. And then finally, this is also a paper that Anthropic has released, so the company behind Claude. They have done something a little bit similar as the Google paper from a couple of slides back, but they have been focusing on tracing the thoughts of a large language model, not with a human, but just inspecting a large language model itself. You can check out the video which they have posted, which is pretty interesting as well. Basically, they have come up with a new interpretability technique that tries to give better insights towards if a language model constructs their output, how far does it plan ahead, basically? We have, or we will see that it's kind of an autoregressive process, but in the first tokens, it's already paying attention to things. So how far or how much does this attention mechanism already take into account maybe later steps that it will have to do? And they have come up with a very clean, very nice system where they indeed show a couple of things. And so the things that they show is that Claude indeed thinks in a conceptual space that is shared between languages. So it has some internal universal language of thought that is kind of language agnostic. It will plan ahead what it will say many words ahead and write them to get to that destination. And it will also give plausible sounding arguments designed to agree with the user rather than follow logical steps. That might be a result of the post-training steps that were taken. Very interesting article. The papers are even more so. They test this out on poetry, on language skills, and so on. Very nice work. Anthropic is doing a lot of interesting things nowadays. I hope they stick around. Definitely read, or don't read their paper, but especially their second paper is extremely interesting. It's just a web page basically. So scroll through this, have a read through this. There's a lot of beautiful visualizations in this as well that you can check out. So it was extremely interesting. And at the very least, you can take a look at the video, right? So that was the news overview. There is way more than that. There's Ghiblification all over the place. There is 3D generation all over the place. But again, enjoy the rest of the course recording.
Okay, anyway, we'll continue now with tooling. Tooling all the way from what we will call in-memory analytics. So starting with basically the assumption of you have, let's say, a single machine, like your laptop, or even a beefy server, but we are not doing anything distributed yet. We are also not really assuming that we have enormous volumes of data, or the velocity of our data is extremely high. We get started basically with the assumption of we have a relatively small scale data set with none of the V's of big data, not volume, not velocity, not variety, maybe veracity could be, but still something that's capable to be handled with like a normal working data science environment. We'll very quickly go through a couple of visualization techniques, and then we'll get started with the road to big data and talk a little bit how this fits in with the parts that come afterwards. And then basically we look at some special, you could say, well, topics in terms of this whole tooling. If you talk about data science, obviously notebooks is one particular piece of software that in data science we tend to use a lot, so we'll quickly talk about that. Labeling tools is something that we can talk about. File formats is also like a small discussion on, well, you all know a CSV file, but probably there are other ways to do that as well. Packaging, versioning, and then also talking a little bit about model deployment. I will not, you will notice that I will not discuss each slide in like all the details because many things are already familiar to you, and this is also more as kind of a reference in a way as well. So think more about the general picture. I always like to start with this landscape slide. This person, Matt Turk, has been doing this for quite a while already. This is still the version from 2023. By now, there is a version, it's actually on the next slide stack, that he has recently, just now, released for 2024. If you would put all of these landscape slides next to each other, what you will see is that there are more and more logos year after year. This becomes denser and denser. You can't read it anymore, even on the 2023 version. The goal is also not to read it. So basically what we will try to do, or I will try to attempt in this whole tooling discussion and platform discussion, is the next time I see a landscape slide like this, can I kind of find my way in terms of, well, what does this mean? Where am I located in? Where should I shop around in, right? How is this organized, and what do all of these things mean, right? Now, what you will always see, in very general terms, there are these two large blocks, this infrastructure one on this side, connected to kind of open source infrastructure here underneath it, but that's also infrastructure. And then like things to make utilize APIs, but that's more, okay, data delivery. So there is this kind of infrastructural side. And then there is this, what's called here, analytics, machine learning, artificial intelligence. So this you could call more the analytics side of things. And that's very often, and this is kind of how we went through the past, by now I can already say, well, more than a decade, how you went through this and how this has kind of emerged. And in the very early days of analytics, back when we were still using tools such as Weka, it was more on the analytical side. Our data sets were not that large yet. The volumes and the velocity was not that incredibly large yet. But we already had stuff in databases in a tabular format. And the question back then is, well, how do I get some insights from this? How do I build like a decision tree? Wow, magical algorithm on top of this and make some predictions or get some explanations based on that. And then we had a rush, a rush came along from the world of the web, from companies like Google and LiveJournal and MySpace back then, right? And Facebook, that were their initial concern was, well, we are dealing with exploding volumes of data and a whole bunch of events per time unit. So per second, or people are posting so many messages and they're doing this, and we need to find ways how to deal with all of that. And that is where big data then grew from, which was then adopted or was taken up by consultants trying to sell all of this stuff to normal organizations and making them believe you also have a lot of data, you're also very important, and you will be able to get way more insights out of this because look what Facebook is doing and Google is doing and Yahoo is doing and so on, right? So a lot of companies jumped in this whole big data infrastructure side of things, but then came to realize, yeah, okay, wait a second, now we have a way to kind of store this data and manage it a bit and play around a little bit with this, but where are the deep insights? We don't really have that. And that was a little bit of a disappointment in this whole big data kind of world at that point, is okay, we now have the big data platforms, but where are the insights, where are the analytics? And then we saw a swing back of the pendulum, back towards machine learning cases, and what you would call today AI, right, is also the result of that swing back more towards the intelligence, the insights. So that's the condensed version of the story. But that's why you see always two sides in these landscapes. You see an infrastructural side, and there they will use words such as big data, integration, architecture, NewSQL, NoSQL databases. So it's about database technology, vector databases, feature stores. It's about streaming data, AI ops, ML ops, but the ops of it, the deployment of it, the management of it, not the pure algorithms, not the pure insight retrieval. So that's one side. The other side is then the analytics. That's this red and purple part here. And those are words such as data science, machine learning, AI. We do NLP, we do computer vision. We use generative AI. Also still business intelligence and visualization, right? Still for many organizations, even today, if their first entry point towards getting more insights from their data and being able to do a bit of prediction or at least understanding, but maybe a bit of forecasting and so on, a lot of it is still versed into business intelligence and visualization tools. Things such as Power BI, things such as Cognos, things like Tableau, drag and drop interfaces where you can fetch tables from your database and push them together into a chart, and then people make like a trend line on top of that, and that's their model, and that's what they show to management to kind of look at how sales are going and so on. Of course, still extremely common, right? Not really predictive because, yeah, making a couple of charts and putting a trend line in there, typically the amount of features that you use is very limited. It's a very human-driven process. You can make a dashboard look very appealing, right? And IBM is good at selling this. They make a white on black dashboard and you can see the ships moving around in the world and look at all this intelligence that you have. Sure, it looks fantastic, but in terms of the model power behind it or the predictive power of a model behind it, well, typically there isn't even a model. What you have is just, you have a fancy visualization. Right? I'm not dissing that, there is nothing wrong with that. Like I said, in many cases, this is the first entry step for companies to do and to get more insights before they start using AI or algorithms and all of that fancy stuff. So this is, in this side, this is about we want to get insights from our data. And that means that there is a difference, right? We have started in this course so far from the analytics side. How do we obtain insights from our data? How do we give explanatory, descriptive, predictive insights from our data? Does not mean that you necessarily need to be dealing with large volumes of data or high velocity data, right? Even from very small data sets, you can get extremely valuable insights, right? The other side of the story is, well, big data is about how do you manage and store huge or high speed or very unstructured data sets. Right? But that doesn't mean, and this is the mistake that a lot of early adopters of this whole big data thing made back in the day, that doesn't mean that if you're capable to do that management and that storage, that you get the machine learning or the AI for free on top of that. Right? And that's why today we have ended up with a lot of companies that have a huge data lake filled with crap, basically, that they haven't been able to get any value out of. Right? Because you can set up huge initiatives with a whole bunch of architects that go looking around in the whole organization who has data in source systems, trying to pump it all into some new kind of storage system, and then what, right? And these initiatives, they never fully are able to come to realization, because by the time that you have maybe pumped 10% of the source data in your new fancy storage layer, there is already a newer, fancier storage layer that you want to utilize instead, right? But this is what architects like to do, right? They like to make pyramids and make drawings of lines and boxes and so on, but not necessarily being able to get insight from that. So, okay, we have talked about the analytics a lot of times already, so now we'll move on to the story of big data, or at least that's our goal so far. Now, of course, you could say, well, this whole big data thing, for me, or in my case, I don't want to concern myself too much about that. A lot of big data will be about, I need to be able to deal with high volumes, but is that still a challenge today? That's maybe a question that you could ask. Is this still so hard to overcome than it was a couple of years ago? You might say, well, I'm dealing with high-speed data. I'm Uber, for instance, and all my customers are traveling around in taxis and they have the app open, and all those apps or these smartphones are sending me events through my API, and I want to do some kind of real-time stuff on top of that. You might have very unstructured data sets, and then, yeah, sure, those will be cases that are pretty difficult to handle. But you could wonder, like, if it's just volume, for instance, is that still a problem? Like, is it a problem that today I want to deal with a 20 gigabyte tabular data set, for instance, and it's not coming in real time, and it's not unstructured, it's just tabular but big, right? So this kind of starts from the assumption of in-memory analytics. And in-memory is basically the default working environment if you open up Excel, or if you open up Python with most of its libraries, or you open up most statistical commercial tools. In memory meaning the RAM memory of your computer, right? The working memory of the machine that you have available, right? And very often, or you might have seen previously that, okay, if you try to open up a large CSV file with pandas, for instance, or do an aggregation, that it gives you an out-of-memory error, right? So that basically indicates that probably we need more specialized libraries for that, or we need to have a big data platform for that. Now, you could say, well, is this really a problem? Maybe not that much, right? And today, maybe even less so than it was before. For instance, if you're an organization and one question is, well, to overcome the memory issue and to be able to deal with large data sets, one way how we will be able to do that is by working in a distributed setup. Instead of working with one computer, we will work with a network of 100 of them, and we will try to distribute both the storage, most likely, but also the workload if we want to do computation. We will try to distribute that over a whole bunch of machines. Or I could also say, well, just invest in one very beefy machine and just stick a lot of memory in that machine and then let your data scientists just work on that machine. What's going to be the easiest to use for someone that already is using Jupyter and Python and Pandas on their local laptop? Well, probably the single beefy machine, most likely. Today, buying such machines are not that expensive. If you compare them to setting up a fully distributed system, maybe not that bad of an idea. Even in terms of computation power, 128 core CPUs, they are coming. You can purchase them already, ARM architecture and so on. They are available. So maybe you don't need to have 100 machines. Maybe you just need to have a couple of very beefy machines. You could also wonder about, well, do we need all of that data? Maybe we can apply sampling, or we can try to be a little bit smart about that. Yes, you might have lots of historical transactions somewhere in a database, right? But do you need all of them to train your model on? If they're more than 10 years old, how informative is that going to be to begin with, right? So also making maybe some smart decisions there can help as well. Speaking of databases, and it's really messed up that a lot of organizations, they didn't realize this. If you ask, where does your data live now? For many organizations, the answer is going to be, it's sitting in a relational database somewhere. It's sitting in Oracle, it's sitting in DB2, it's sitting in MS SQL, it's sitting in Postgres for some of them. How do you manage it there, right? Same question. Well, it might be a couple of machines, but typically also not fully distributed or extremely distributed. And if it doesn't fit in memory, these databases are smart enough to execute queries in such a way that A, they swap out stuff to the hard drive when they need to, right? So you do need to make sure that they have a lot of off-memory storage available to them, but typically that's what the database administrator, what that person did. And secondly, to speed up the queries themselves, we built indices over our data, right? Well, isn't this sufficient? Why not just use your relational database then? If your data already fits in there and it's workable in there, do you really need to move all of the data to a distributed platform and expect better results from that, right? So also the idea of this relational database being a help there was, for a moment, was forgotten. And it's a bit strange that it was forgotten, and it was mainly forgotten thanks to nice sales pitches that told people that this new way would work way better. But kind of these mechanisms that we had already from that world, mainly disk swapping and efficient indices, is something that actually we can also utilize for the computations that we want to do. Maybe the key is that the environment changed a little bit. Data scientists, they wanted to work in Python, and then you come from Pandas, and like a typical relational database administrator, they're used to working with SQL, right? And maybe they didn't talk sufficiently enough. But for a second, we lived in kind of a little bit of a strange world there, where we kind of forgot what happened in computing for years before. So now, today, we have learned a bit of lessons from that. And so actually today, I think that many people would advise you, you definitely can, but would advise you to take a good look at what makes your data big. If it's just volume, and the volumes are reasonable. I mean, you need to talk about a petabyte scale to really say, okay, you have volume, right? But if it's terabyte scale, gigabyte scale, you don't really have volume. That can be maybe solved in different ways today. If it's about high speed, if you're the next LinkedIn or the next Uber or the next Facebook, then yeah, sure, right? If it's about enormous unstructured data, if you're Google and you need to crawl the whole web, then yeah, sure. But how many typical organizations work on the scale in terms of data requirements like Facebook does or LinkedIn does or Google does or whatever, right? They probably don't, right? So it's also having a little bit of honesty there, and which is lucky, right? That means that you're not facing those problems that the organizations faced. But again, the mistake of the early adopters. Now, looking at in-memory, today, the big two are Python and R. And to be very honest with you, the key reason why I still include R here is because I have a certain let's say, affiliation or a certain positivity towards our users, so I still include it, but I think that many organizations nowadays, they have made a choice for their data science environment to go with Python. Doesn't mean that others don't exist. You have places where vendors like SAS or SPSS remain as well, remain being utilized. Although a lot of organizations have made initiatives to jump away from that or to go or to step away from that because of the high licensing costs. Very often it's more what keeps them with those vendors is not really because of an algorithmic advantage that they have, but it's more about support that you get from them, or it's more about like vendor wall-in, like congrats, you have stored all of your data into SAS7 BDAT files and you can't get it out anymore or not so easily, so you're not kind of stuck with them. Or your models run on top of that on Enterprise Miner and now you're stuck with that. There are other languages that have been up and coming as well, like Julia, like Mojo, for instance, which are very interesting new initiatives, but they didn't reach such a high level of adoption in industry yet, right? Especially if you stick in these regions, I think most people will expect you to have some Python knowledge and how to utilize Python, perhaps R, perhaps SAS, perhaps SPSS. Julia, less adopted, Mojo, still far out. There are a couple of places where maybe Scala might be good to know about, especially if it's an environment that's very heavily Apache oriented, so Spark oriented or Hadoop oriented, but these are definitely the most important ones. Important, and especially for Python, there is nothing magical about Python making it a perfect language to do data science with. It is a very good general language, and that's why there is often the quote, Python is the second best language for everything, but it's not the best language to do machine learning with, not at all. If you wanted to have a better language, then maybe something like APL or Julia or Fortran even would have been better suited. But it is a very easy to learn generalistic language, and what makes it powerful is not the language itself, but is the whole ecosystem that has popped up around that language. It's the availability of libraries that you can access through Python that has made it so popular in the space of machine learning, right? Libraries like TensorFlow, Keras, PyTorch, Scikit-learn, XGBoost, CatBoost, LightGBM, you can all access those from Python. So it's kind of the universal language to get access to interesting things. If you just install Python on itself, you can't do anything in terms of machine learning. You're never going to implement a machine learning technique or algorithm, even if you would like to come up with your new idea or something like that, you would never implement it like in pure raw Python. Your first step would be to have an expectation that you have NumPy available, right? Or maybe a GPU-backed tensor operation library, like Torch, for instance, like PyTorch. And on top of that, you will probably have expectations in terms of, well, you want to make that faster, so probably you will end up writing your little algorithm or library in C or C++ anyway, and just call it from Python, right? There's still today a whole bunch of libraries that Python is using and that R is using that themselves are written in Fortran. Like the library to do linear algebra on virtually every sort of CPU architecture today, a BLAS library with things such as OpenBLAS, are all implemented using Fortran code, right? So not in pure Python. You just use Python to interface with those underlying libraries. So nothing special about the language, it's about the ecosystem that has popped up around it that makes it so suitable. Typically what you will find in terms of libraries is something to work with higher order arrays in a way that is faster than what the language offers out of the box, and in a way which allows you to do more in terms of mathematical operations that you want to do with these matrices or tensors, as you could call them. Of course, in Python, you have a list, and you could make a list of lists and then call that a matrix. Newer versions of the language have support for like a matrix multiplication operator, but just the fact that it took so long to be introduced kind of illustrates that, okay, then the next step was for you to implement matrix multiplication yourself using a function, and it went horribly slow, and you would basically be looking for like an alternative there. So one library that you will that you will often utilize is something to work in a fast way with higher order arrays. Typically, this backbone, this structure of tensors then provides a basic support for data frames. So data frame is an assumption that says, okay, a data frame is not just a matrix. It is like a matrix in the sense that typically it has rows and columns, and the rows represent instances and the columns represent features. But contrary to a normal matrix, the columns in a data frame can be of a different type. So you have a numerical type, and you have a categorical type, and so on. And then typically you also expect some basic verbs or operations that you can execute on those data frames to play around with them, filter them, sort them, aggregate them, and things like that. That then will typically form the basis for the implementation of algorithms. Like, okay, now that I have a data frame, now I would like to play around with a supervised technique or with an unsupervised technique on top of one of these data frames. Tabular data is the assumption then, but then you're mainly 90% of the way there, right? And then maybe something that you need on top of that is a way to plot results and visualize stuff. So a plotting library, a visualization library, a charting library is then also something that you typically expect, right? And if you combine these four things, you basically get like the standard mini package that you, or set of libraries that you would install in Python or to be used in Python to get started with in terms of doing data science. So just installing Python itself will not give you sufficient stuff to do data science with. I remember a long time ago in the old days when data science was up and coming, and I was doing contract research that IT at a large bank asked me, what do you need? I said, Python. Okay, here is Python. It was just Python. I can't do anything with that, right? In R, you could say it's a little bit different because there, at least when you install that, the language itself has a bit more of functionality built in. Mainly it has the native concept or a native concept of a data frame. So that's already positive. The negative is that it's not really a very fast or efficient implementation of a data frame. So in most cases, people will also install an add-on library in R as well to get a faster data frame, basically. But at least there you get a bit more out of the box in terms of support for what you would expect as a data scientist. In the R world, there typically what you then add on top of it is comes from this whole tidyverse driven by Hadley Wickham, also the founder behind RStudio. You could say he's the driving force behind modern R. Things such as ggplot2 for visualizing data, dplyr and tidyr for manipulating data. R's datetime support and string support is kind of horrendous out of the box, so also there add-on libraries to make that easier. And then maybe a whole bunch of libraries to read in external files that you have in all sorts of different formats. So this tidyverse, basically today, if you still would plan to learn R nowadays, the recommendation is typically, well, make sure that you use the modern R principles. A tutorial that starts, I mean, it's interesting, but a tutorial that starts from let's install R and let's use the language like purely natively, and let's not use anything that comes from this tidyverse, it's going to feel like it works a little bit against you. It's going to feel a little bit archaic, right? So most people, they assume, okay, we need this tidyverse. Why? Well, one of the things that made this so famous, the operations, for instance, that dplyr added is it added typical data wrangling methods in a way which are easier to write down than you would do with base R. So you could do this with base R as well, right? In many cases, it already combines functions that are available in base R, but it allowed you to write them down in a way which is, let's say, a bit more readable, in a way that almost looks a bit more like SQL statements. So for instance, flights might be, and this is still something that makes R, together with these packages, quite well suited for quick data wrangling. Flights here is a data frame that's been loaded in, and then basically this pipe operator, comparable to a pipe operator from POSIX or from Unix, basically says, well, take the thing on the left-hand side and pass that in as the first argument on the thing on the right-hand side. So flights will be used as the first argument in here in select. And then what do I want to select from flights? The year, the month, and the day column. Then I want to give that result to arrange, and I want to arrange by year descending. And then I want to take the top 5 rows from that. So it makes it very easy to write stuff like this down. It has a lot of very nice benefits. The fact that you can link this thing to a database that you already have, and that this will avoid you to first have to make an export from the database into a CSV file that you then load in on your own computer, and you go, oh, strange, it doesn't fit in my memory. That with this thing, you can just basically connect to that database that you have already, write the same statement, and dplyr will be smart enough to convert this to SQL in the back for you automatically and execute this on the database server. Again, it's a bit strange if you look at newer technology or newer libraries in Python, like DuckDB, for instance, that these are basically also just implementing this, and this is actually things that we knew about for quite a while already. You have a relational database, it's good at data manipulation, it's good at data wrangling, do it there. Don't download a 50 gigabyte CSV file and try to do everything with like a single laptop, right? So those are good insights that this already had at the time. So lots of benefits on that. If you want to learn more about dplyr, you can check out the cheat sheets there. But for like these kind of operations, quite pleasant to work with. So then you have a data frame concept. You have a way to manipulate that, to wrangle with that, to play with that. Then typically once you have done that, you will need something that says, okay, can I now execute, like, can I train a model on this data frame that I have here? So also here, of course, you have a couple of choices. Now, OR had a bit of an issue that it's a language by statisticians for statisticians. So every person that came up with their own algorithm, they basically released their own library in OR. But there was not a lot of, let's say, standardization in the way how these libraries should be built. So already for random forests, for instance, there is not just a single library that you can download. There are like about 3 of them, and they all differ in the sense that, okay, what is the function called to train a model? Is it called train, or is it called model_train, or is it something else? So they all take kind of different approaches on that. Let's say that I want to compare 5 different models. I want to use both logistic regression and a decision tree and a random forest and a boosting model and a neural network. Then you basically would have to rewrite your code 5 times because they all differ slightly in the way how they're being called. Obviously, people didn't like that. So a whole while ago, there was a group of people that came up with a package called Carrot, Classification and Regression Training, that said, look, we are not going to build our own algorithms, we're going to take what already exists, but we are going to build a unified layer on top of all of these underlying libraries so that you can call them and utilize them in a standardized, unified way. Right? Very helpful, obviously, because then you had a single way to say, I want to train this type of model with these hyperparameters without having to relearn how every underlying package worked separately. Now, Carrot is not perfect. It's still, if you work with OR, you will still find that this is the most used one in tutorials and references and so on. But it's certainly not perfect. Like things that you could say that it doesn't have is unsupervised models or not in there, for instance. But okay, fine, that's not really predictive, you could say anyway, but okay. Setting up a pipeline in terms of the thing that we discussed previously, where I said, well, the thing that you should do first is split your data into a train and a test set, and then set up your whole pipeline, including pre-processing steps. That's something that Karen doesn't do that well. And that's also why in a lot of tutorials you will see things such as, first we're going to apply PCA, and we're going to apply it on the whole data that we have before splitting it into train and test. Whereas we know that that's not really ideal. But that's also because Carrot makes it a little bit challenging to do it in the correct way. So learning from packages coming from Python, for instance, other groups also found that, and they have come up with alternatives, packages such as MLR, which is like an initial attempt to do something better, but was not that great. So then they quickly changed it to a new version, which is done, and this is still the most recent version, called MLR3. So maybe today, if you would learn something from scratch, maybe it wouldn't be Carrot, it might be more suitable to learn MLR3. It takes a more object-oriented point of view as well, rather than a functional or procedural point of view, which some R people also don't like because they're not really programmers, so object-oriented stuff is not really their forte, but still I would say it has a couple more benefits than Carrot does. There is also a package called Model R, which also comes from this tidyverse, but it's mainly suited, or it's mainly developed towards making simple regression style models that you then combine with a visualization. So it's not such heavy duty. It's not going to, don't expect that you will build XGBoost models from there, or that you will, like, even a decision tree. It's like for trend lines and simple forecasting setups. But it plays around well with the other parts of the tidyverse. So if you use dplyr first and then Model R, and then you want to make a ggplot2 out of that, it's pretty easy to do that. And in that sense, one of the books which is still very nice as a starting book is this one, R for Data Science. It's free to read online, and it follows a modern R approach, and it keeps it very simple. It first teaches you the language and some standard operations before like diving into all the supervised algorithms. So for basic data wrangling and playing around with data, this is actually a pretty good reference. There is also Tidy Models, another collection of packages for modeling and machine learning, also using the tidyverse principle. So contrary to ModelOr, this is one which tries to do a little bit more in terms of supervised analytics. So Tidy Models, it's still relatively new. So it's a little bit, you could say, in development, but it also tries to offer a unified interface, and it's also not bad. They set up what they call recipes, which we would call pipelines in scikit-learn, basically. And from recipes, you create a workflow, and basically this is the way how you define, well, I want the model, and the model that I'm going to use is Ranger, which is an implementation of a random forest model in R. I want so many trees, and this parameter, this is one that I want to tune. This parameter is also one that I want to tune, and I want to use classification, or I want to use it as a classification model. This is my recipe. This is kind of what I want to predict. This is the data set that I will utilize. Arrival data, I want you to convert to a date, and so on. From there, I make a workflow, and then I can say, well, now run a tuning grid and find me the best model in terms of hyperparameters on this data set. Also not a bad package. So again, today, if you not know any R and you would have to utilize something, maybe Tidy Models also a better choice than Carrot. It looks a bit more verbose. There is more kind of code involved, but overall the architecture is cleaner and the abstraction that they use, or abstractions that they use, are better than what Carrot offers you. In terms of visualizations, pretty quickly, the most important one, kind of the trendsetter in terms of a package, and also something that R does very good actually, is ggplot2. Mainly because of the fact that they adopt what's called a grammar of graphics approach that they didn't come up with themselves. It's something that they adopt. But the grammar of graphics is basically a way that helps you to deconstruct a chart, right? So it's not for general purpose visualization, but to deconstruct a chart into several components. So they say, well, you start with the data, and on the data you apply certain aesthetics, what should be on the x-axis, what should be on the y-axis, and so on. On top of that, you want to add in geometry, like what should the points look like, what should the lines look like? Does your chart have facets? So do you have different subcharts, yes or no? Do you want to apply overlaying statistics on top of that, like a trend line? And then the rest is, well, what's the coordinate system that you utilize, and what are the colors that you like, that you want to apply? And basically their idea is that they say, well, to go from one type of chart to another type of chart, basically we would like to set it up in such a way that you only need to change a couple of these things here to very easily switch between the types of charts that you have, that you don't need to rebuild everything from scratch the whole time, because you're coding your chart here, basically. You're not dragging and dropping it. So we describe a chart in code, but in a way which is cleanly split up into these different grammatical layers. ggplot2 was something that could only produce static results. Of course, we work on the web, so we also want interactive charts and on render targets that are not just a PNG file, but also something that like works in a web browser. So ggvis2 basically bases itself on ggplot2, but aims to work with interactivity and different render targets. And from there, you get packages such as Shiny, which then take this and say, well, now that we have this, we have kind of a tool to make like a whole dashboard on top of that. So you can basically in R make like a complete like a BI style dashboard yourself as well. Now Shiny, the way that it sets up its dashboards, but some Python packages do that as well actually, it uses a style of programming which is called reactive programming, which again is a little bit tricky to wrap your mind around if you've never seen that before. A lot of JavaScript libraries like to do that as well, but in essence it's not so difficult to utilize, and you can kind of quickly whip up something together like this without too much work. For our users, it's actually a pretty good way if they want to quickly show some results to stakeholders and have them play with like a proof of concept kind of dashboard, maybe not a final one, but just so that they can validate the results and play around a little bit with it. This is actually a great way how to do that. And then other packages, well, there are a lot, obviously. Here you see some of the more popular ones. Yeah, weirdly enough, I think I already mentioned this at some point, but like one of the first things that people will look up when they work with R and they've made their first model is how do I make an ROC curve? And again, you can do that yourself, but that's not so fun to do, because then you need to first make that table and then you need to put the points. So you want to look for like an easy function that does that for you. It's not built in, but again, there are like a lot of packages that have it. ROCR, verification, PROC or MLTools are all packages that allow you to plot an ROC curve. And many other style of evaluation curves as well, accuracy curve, PR curve, and so on. They can do that as well. Time series analysis, Forecast is a very good package for that. Prophet from Facebook was very popular for some amount of time, but has fallen out a little bit out of popularity these days. But Forecast is still a very good package for that. Social network analysis or iGraph is pretty much liked for that. And then some of the packages that I already mentioned as well. So for Python, you get a little bit less out of the box because there even a data frame is hard to load in if you just work with Python purely. So there we need even a bit more to get started with. And there the traditional set of packages that every data scientist expects nowadays is still SciPy, NumPy, Pandas, Matplotlib. That's like the group of 4 friends that you see all over every installation where Python is being utilized for data science. SciPy is an ecosystem of implementations of things that you need in mathematics, science, and engineering. It's actually a very broad package, and it has a lot of stuff. It has optimization functions, it has things to find the roots of a polynomial, it has things to help you, maybe you want to run a simulated annealing optimization, you can find it in there. If you want to find the convex hull of points in 3D space, you have an implementation in there. So SciPy is a very broad package. If you want to calculate a pairwise distance matrix, you have things in it for that as well. So typically you will not end up utilizing a lot of what's in SciPy, but having it installed, you will always utilize something from it. NumPy then is kind of the a daughter package of SciPy itself, actually, or came outside of the SciPy world as well. And this is what implements n-dimensional array objects. So the question or what this package actually wants to offer is, yes, we know that Python has lists, that it has arrays, but they're extremely slow, and they do not have support for linear algebra operations or broadcasting operations. So we will implement an n-dimensional data structure where you can put numbers in a way which is fast. In a way which is still bound or operated or executed by the CPU. Newer packages such as JAX and such as Torch, PyTorch, they do the same thing. They also implement a tensor structure, and a tensor is just an n-dimensional array, but they have the GPU execute the operations. If you have a GPU, typically you will even you will get a speed boost from that, right? Now, NumPy is so popular and is so widely utilized in the Python ecosystem that also every other package that implements tensor operations like JAX or Torch, if you know NumPy, it's going to be very easy to switch to one of these other libraries. The function calls are mainly the same. They have the same names. They have the same arguments. You will not have to relearn a lot. Another package then, which is called Pandas, says, well, let's take NumPy, right, as the underlying data structure. And we're going to represent lists of stuff. We are not going to work with 3 and 4 and 5 dimensional arrays, so we'll have lists and matrices. But on top of that, we can then implement our data frame. And our data frame is basically just a matrix, but with a couple of additional elements around it. Like every column has a name, and maybe we have an index describing all of the rows, and maybe the columns can have a different type, so then we need to split that matrix up into different lists. But virtually you have most of it already, and on top of that, some easy-to-use functions, again, to sort the list, to make an aggregation, to do a filtering, and things like that. And then you have a data frame concept in Python. And that's why Pandas is utilized all over the place, why that's in every notebook that utilizes Python. You will see import NumPy SNP and import Pandas SPD because everybody utilizes them. It's gradually changing, like I said, for NumPy. Some people like to use these instead because then you can work on the GPU. For Pandas, some people are switching to using things such as Polars or things such as DuckDB. And mainly because that Pandas, it has changed in the latest version, but for a while Pandas was not the most efficient implementation in terms of dealing with large data sets or executing operations in a way which is relatively fast. More about it in a second. And then we still need something for plotting, right? We are going to make charts based on the data wrangling that we do. So there, the favorite is Matplotlib. It's not as fluent or nice to read as ggplot2 is. ggplot2 is more declarative. I tell you what type of chart I want to see. Matplotlib is way more procedural. It's way more, well, tell me how to plot it, right? Don't tell me what you want, tell me how you want me to plot the result, which some people, especially if they come from the R world, also see as a critique towards it, like, oh, this is way more difficult to utilize. Matplotlib is more inspired by the MATLAB style of plotting. A lot of functions that it implements or were taken from the way how MATLAB does its thing. So here you can see an example of this broadcasting operation in NumPy. For instance, basically it allows you to express things such as, I have a 256 by 256 by 3 matrix. You should allow me to just say, well, I want to multiply all of these numbers there, and I don't give you like a 256 times 256 times 3. I just give you a vector of 3 numbers. And then you should be smart enough, basically, this is what this broadcasting do, to then say, for every pixel in the image, you want to multiply the red number by this, and the green number by this, and the blue number by that. Right? And so apply this multiplication, broadcast this multiplication with this vector of 3 numbers to every pixel in the image. You can't do that easily by just typing normal Python code with lists. So with NumPy, these operations, these algebra or algebraic operations become very easy to express. And that's what it basically offers to the table. So if you work with NumPy, you will see that it's a very well-designed library. If you work with matrices and tensors, it's very easy to read through, and it's very easy to understand the documentation. Pandas, and especially its API, is a little bit of a mess. And again, this grew from historical reasons, but you will see that in Pandas there are like a couple of different ways to do things. Even selecting something from a data frame can be challenging, because you will read, well, there are different ways how to do that. If you have something called df, if that's your data frame, so df is a pandas object, you can do stuff such as from df, take a. And that makes it look like a normal Python dictionary. Is this then the row with the index name a or the column a? There is also df double brackets a. Wow, what is the difference? There is df loc column a. There is .iloc, there is .add, there is .iadd, there is .ix, there is So there is a whole bunch of ways to just even select rows and columns from a data frame. And sometimes confusing, right? Confusing in the way that if you type df1 to 2, it gives you the second row, but df1 gives you an error, and df double brackets 1 gives you the second column. So this makes people go, whoa, what's going on here, right? And that's why articles have been written such as minimally sufficient pandas that kind of tell you, do it this way and stick to this way, right? And the way that most people will recommend you is always use .loc, right? And except when you really know you want to work with integer positions, then you use .iloc. Don't use any of the other things. So do it with .loc. And with .loc, you can express what are the rows that you want to select and what are the columns that you want to select. And then it looks similar to how you would select or slice from data frames in R, and without too many kind of surprises that you will get out of there. Now, once you know kind of the way how it's set up, it's not too bad. It does have strong support for working with time series. The reason why is that the creator of Pandas, he was a quant. So he worked in quantitative finance, so obviously they work with a lot of time series data there. So Pandas has quite good support. And also what we should say, or what I should say, is that in recent versions, the documentation has been cleaned up, has become easier to read. So at least it's easier to find the right answer if you have questions there. Now, we don't have anything yet for supervised or unsupervised learning. We just have a data frame. And like I said, also there you see that, well, there has been a little bit of competition in the space. For instance, a relatively new package is Polars, which is a fast data frame library for Rust, but typically most of the users will also still or will continue to work in Python. A package that basically follows the Pandas API in a lot of ways. So again, there will not be too much that you will have to relearn, but one which is way more efficient than Pandas is. And I think that a couple of weeks back when we discussed the in the news article where people did a meta-analysis of Kaggle competitions, that they saw an increase in people adopting Polars versus Pandas. So it's actually also not a bad look to basically now say, well, maybe let me just learn this. It's going to work faster. It's going to be better to handle large data sets. Maybe I should do that instead. Another one, and you can see some benchmark results here. They're already a little bit outdated, right? They're from a couple of years ago. But they already show that like there are better packages on the market than Pandas. Like for basic questions, for instance, you see that Pandas is all the way over here, right? And then you have Spark, which is a bit better, but you have Polars, which is kind of the winner there. ClickHouse is another one which is quite popular, which is also an open source. It does more than just data frames. It's a whole kind of database environment. You have others like Dask and so on. But like generally, Polars does a good job. So maybe worthwhile to take a look at that. Another package that I really like is DuckDB, especially nowadays. It follows more of a SQL style of querying rather than writing Python code like this. But in the end, all of these operations, they work like SQL anyway. So if you look here in the documentation, one of the client APIs is Python. You can also use it in R, by the way, and then you utilize the relational API. Basically, they say, well, you can wrangle or play around with your data by making queries, basically. So you don't write .select, .filter, .arrange, but just learn SQL. By the way, if you would not know SQL already as a language, it is still one of the best languages to learn if you plan to do some data wrangling, because you will see it all over the place. Very likely you will in your life have to work with a database, so you will have to know a bit of SQL. So it's a very good language to know about in general. And you see that DuckDB basically uses it as its main query language. But it's also a very fast one and it works quite well. Ibis is another one. And this is typically what you see. I wouldn't necessarily recommend this, but Ibis basically said, well, now that there are all of these data table or data frame packages out there, like you have DuckDB and ClickHouse and Dask, and maybe your data is in a traditional database, or it's in Druid, God forbid, or it's in SQLite, it's in there stored somewhere, or it's in Pandas. And you want to be able to utilize all of these, but you don't want to learn every package separately, because yes, they look alike, but they have like some small differences. Well, then learn Ibis, and then you can use whatever backend that you want to use, because we translate to these things. So this is kind of a unified data frame on top of all of the underlying data frame libraries. Yeah, not too bad. I mean, the necessity is there. Like they give some examples as well. So again, if you know Pandas already, it has kind of very similar operations there. And you can still convert to a Pandas data frame, because people realize that in the end, that's what you will want to get out of it in most cases anyway. But also interesting to learn, but they all offer similar operations. Filter, sort, arrange, aggregate, basic SQL commands. But they can differ quite heavily in terms of efficiency and speed, right? I have seen cases where making an aggregation on like time series data in Pandas took hours to run, many hours, and switching to Polar sped it up and it was done in like 10 minutes or so. So again, exploring sometimes other options is not a bad idea. Now, then going to modeling, of course, in Python, scikit-learn still uncontested in terms of implementation of supervised and unsupervised techniques. It uses NumPy, it uses SciPy, it uses Matplotlib. It's open source, so companies can utilize it because it has a BSD license. Lots of algorithms implemented. It's still best in class. Some people diss it a little bit in terms of, well, why would you still need it if you plan to utilize XGBoost or CatBoost anyway? True, but even CatBoost and XGBoost implement scikit-learn compatible implementations of their models, so that makes it easy to then combine with other stuff that you would need from scikit-learn anyway, for instance, to do your pre-processing with, right? So it's still very popular in the space, and it has been since its conception. There are alternatives. If you really come from a more statistical world, then you might find that some forecasting techniques and so on, or some regression techniques especially, are not implemented in scikit-learn, and it might be worthwhile to take a look at stats models, right? Again, it's not so or you will not find the same depth of broad of models or techniques that you would maybe find when you would be using OR as a statistician, but maybe you will find it in stats models. Then there is also PyCaret, which tries to offer something similar to scikit-learn, so also like a simple library that that allows you to do like supervised modeling in Python. I don't like it that much personally. I know that some people have utilized it. I think it has some things in it that make it very easy to make mistakes, so I would be a little bit careful with that. I'm not a huge fan, but I mean, it doesn't do anything intrinsically wrong or something, but just some of the API styles I don't really like that much. So here you see an example in scikit-learn, but you guys know how that works. There are things, of course, that scikit-learn doesn't do. Yeah, general structured learning, sequence-based learning, association rule mining is something that we also saw, is also not something that scikit-learn does. Two other things that stick out a bit, recommender engines. There are other packages like Surprise or LightFM that might be better suited. Now, again, to be quite honest with you, nowadays, even for a recommender engine, it's not that uncommon for people to utilize XGBoost or something like that to do that with, right? Then basically every instance is a pair of a user and a movie, and you have features of the user and you have features of the movie, and the question is just, well, predict me whether it's a match. And then you will ask the question, yeah, but it's not just about predict me whether it's a match. The evaluation is we can only give the top 5 movies and we want to have as many matching as possible. The rest of the recommendations don't matter because we only show the top 5 on the front page of Netflix. Well, then we saw before that you could switch to another loss function when utilizing XGBoost, which is more suited to work in a ranking context like that. So very specifically developed recommendation engines, like based on user to user and stuff like that. Very often people utilize the same techniques anyway. The same goes for time series as well, to some extent. Like again, you can use the time series stuff from stats models or Prophet, which also exists for Python or is available for Python. But also here too, very often you will see that people in industry or in practice, they will just create lagged features themselves and just stick it into an XGBoost model and do it that way. If you think about what Arima does or things like that, I mean, it's auto-regressive, so basically the whole idea is let's take lagged features and use them as features. So you can do that manually with any sort of model at the end of the day. Now, one thing that is certainly true that you will not do with scikit-learn is once you go towards deep learning, you will not utilize scikit-learn for that. It has a basic MLP implementation, trains on the CPU. You will rarely utilize it. If you really want to work with image data or video data or audio data or text data, well, it has text mining support, but like you really want to do like training using deep learning models on the GPU, you will not use scikit-learn. Then you will use TensorFlow, Keras, or PyTorch nowadays. You won't utilize scikit-learn. In terms of visualization with Python, yeah, the problem with Python is not that it doesn't have enough visualization libraries. The problem is more that it has too many visualization libraries. Now, a couple of them do stick out as being more popular. Like I said, Matplotlib, that's kind of the foundation. Seaborn is also something that a lot of people like because people have noticed that there are some things that are that should be easy, but that are surprisingly difficult to do with Matplotlib. And then Seaborn says, well, let's make these things, these couple of hard things that people want or utilize a lot, let's make them easy too. So we work on top of Matplotlib, but we offer like a little bit more basic functionality. Like something very typical that you will find is if you would ever search for it is, okay, I have a matrix of numbers, or I want to make a correlation plot, which is basically, okay, I have my numbers in a matrix setup and I want to make a heat map on top of that. I want to visualize each box from red to blue based on the value of the number. Difficult to do in Matplotlib out of the box. With Seaborn, very easy to do. There are a lot of whole other ones, like ggplot tries to implement the grammar of graphics in Python, but it doesn't work that well because Python as a language is not as free-form as R is as a language. So, but R as a language is also a bit strange in some aspects there, but it doesn't work that well, so it's not so popular. Then you have also packages. Yeah, if you ever ask the question, like, I don't need to plot 20 points, I have geographic data and I need to plot 20 million points. What Matplotlib will do is it has like a drawing canvas and it uses the CPU to position all of these 20 million plots, and you will have to wait quite a long time before this thing has finished rendering. You will not have like very easy ways to drag this plot or to zoom into it. It's going to lag quite a lot. So you also have libraries that really utilize GPU-based backends to do plotting if you really want to make beautiful artwork or stuff like that. So things like Data Shader, for instance, allow you to do that. And they typically utilize GL backends, WebGL or OpenGL, or maybe even DirectX in some cases if you use Microsoft-based tools to improve the plotting. Most day-to-day cases, Matplotlib and Seaborn, however. And then there are packages for, like again, you have a lot more if you want to work with, if you want to utilize SMOTE and things like that. You have that package Embeddance Learn, semi-supervised models, multi-label techniques, and so on. So also here, this is kind of an illustration of Python as an ecosystem is enormously large, and every day new packages appear that you can find. In the news, we had a couple of them already. So this is what makes these languages work. Nothing about intrinsically the language itself, but about the fact that they have been able to set up such a wealth of additional tooling that you can utilize, right? That's the key thing. There is even unholy stuff such as reticulate, which allows you to call out to or from Python. Be careful when doing things like that, right? You can really make this into a bowl of spaghetti and a complete mess. So typically try to stay in the same language environment if you can. Language interop is not so fun to do. Now, we already had a couple of visualization tools. Contrasting this, what we should also say is you have general purpose tools that are specifically built for visualization as well, the packaged software, and then you find like the typical BI tools, right? You find your Tableaus and your Qlik and your even Excel or Power BI and things like that. Typically what these tools offer are like easy to use drag and drop interfaces, but you don't write code with them. So like reproducing a plot will not be as easy. You just use the tool basically, right? What you will also see is that if you really go into more niche settings, you will find more niche tools for doing that sort of visualization. Like if you're heavy, and we will see that if you're heavily into visualizing graphs, for instance, then you will use specific libraries and or tools to do that. You will use things such as Cytoscape.js or Gephi or Sigma.js. If you're into mapping, you will use specific mapping libraries to help you with that. Libraries that can load in shapefiles or that can call out to OpenStreetMaps because you want to have like the satellite background behind something. So typically for these things, you will find more specific tools if your visualization is more specific. Yeah, a couple of other things here. D3.js is a JavaScript-based library, so it's completely different than Python R. It's meant to be utilized on the web. But it's also quite popular because, well, if you work on the web and you want some interactive plots and you want to do that in a way which is pretty clean, then D3.js is very popular. The New York Times utilizes it for a lot of its visualizations, for instance. You can find some examples on these web pages. It's still also a very popular library to make visualization pages with, visualization web pages with. Plotly and Streamlit in the Python world are also pretty popular as dashboarding tools, especially Streamlit. Data scientists, they tend to utilize it very often. They have a model, they want to expose it as an API, they use FastAPI to do that, and then they build a very quick Streamlit application for people to play around with the model, maybe to call it and play with sliders and to see what results look like. Comparable to Shiny in the R world. It was acquired by Snowflake. Snowflake is a cloud database vendor, but it's still available for use, so it's still quite popular today. GraphViz is a library utilized for graph visualization and diagram visualization. Surprisingly resilient in the sense that it's extremely old, but it still shows up quite often, maybe not as something that you will use directly, but something that's utilized under the hood as the engine to help lay out a graph. So GraphViz is then typically the tool that you will ask, hey, I have a graph here with a whole bunch of connections. Can you tell me where I should put each node in a way so that it looks appealing to the end user? But then I will still draw the graph myself because your way of drawing looks very old. I just need the positions, basically. But a lot of tools utilize GraphViz under the hood to do that. So then you have what you could basically describe as your standard working setup. You can load in your CSV file, you can utilize pandas, you can utilize scikit-learn, and you can utilize your own laptop, and nothing is that special yet. Then the next question is, okay, you encounter your first large data set, what do you do then, right? And this brings us then to the road of this big data discussion. First of all, if you live in the world of on GPU analytics, so you're doing deep learning, then there you might find that you can kind of ignore the question a little bit, because yes, you have here situations where you also want to distribute the compute, right? So typically you have two things to worry about if you are dealing with larger data sets. One is I need to find a way to store all of this data in a distributed fashion on multiple machines because I have so much of it, right? Now, today, you can buy an external hard drive of 4 terabytes, right? If you need more, you buy more external hard drives. If you really have petabytes of data, then yes, fine. Buy a container or a couple of containers and store your data in a distributed way, right? But storage is something that we can basically live with. Another aspect is then I need to do compute on it, right? I have a huge data set that I want to load in and compute something on it. Pandas is crashing, so what do I do instead, right? Well, on the GPU, basically there, well, even compute, maybe I want to distribute it on a couple of GPUs, but typically there you see, well, the problem for most of us, we are not that rich that we have multiple GPUs. And so the training happens in a way which is already batched anyway. We are already used to splitting up our data into mini batches anyway. So for every mini batch, we read that in from disk, we send it to the GPU, we train on that, we take it out of the GPU. We send the next mini batch, we train on that mini batch, we take it out. So we don't typically run into the problem of things not fitting in memory there, right? If it doesn't fit in memory, typically you make your mini batch smaller, right? So anyway, there we are stuck to what fits in the GPU's memory. And yes, you could distribute it over multiple GPUs, but basically the problem appears less often in that case. You might still want to work with 1 million of images, for instance, but even there, they might not be necessarily stored in a distributed fashion. You just have them on your hard drive somewhere. Also, something that we have seen, at least today, is you could also say, well, why don't we apply kind of this idea of mini batching on top of pandas, for instance? Like if you need to make an aggregation, why should you have to read this complete data set in memory all at once? Why not go over it batch by batch, for instance, right? In any case, that's what a relational database did also to begin with. So let's just reutilize those concepts. They also do swapping from and to disk. And so the early attempts to do that, like these kind of ideas of these memory mapped files, and or you have ideas on that like FFmpeg big memory and things like disk frame, but they don't work that well. But nowadays, we have seen a couple of approaches that work relatively well. And a couple of popular ones are Dask in Python, which works very similarly as pandas, but performs this disk swapping. So it's intelligent enough to see, you want to do a group by operation on a data set of 2 terabytes, well, of course, I'm not going to be able to load this thing in memory all at once. I will have to do that like in an operation which is batched instead. DuckDB can do that well. Polars can do that well too, right? So that's why more people are kind of stepping away a bit from pandas, is because we need this disk swapping mechanism on top of that, right? And again, this is nothing new. This is basically a return to what the relational database world had already taught us, right? But it took quite a while for us to realize that. Also here, if you utilize this, nothing forces you to kind of utilize a distributed setup for this, right? Your only problem is that your memory is limited, right? We are not talking yet about distributed computation. We can still do that with the single CPU that we have in our machine. Now, to some extent, you can probably imagine that there are likely ways, if I want to perform a certain operation on a huge piece of data, ways that will be more efficient versus ways that are less efficient, right? More efficient will mean if I have a couple of CPU cores in my machine, well, the more that I can utilize all of them together, the better. If there is 7 cores waiting around for the next piece of data to be loaded in from disk to memory, it's not very efficient, right? Efficiency is also, well, how can I avoid looping over the same data multiple times? It's also about how can I make sure that maybe I have additional secondary indices that can tell me, maybe I order my data on a primary key column or an index column, but maybe now the user wants to sort based on a different column or do an operation based on the ordering of a different column. Maybe I can use a secondary index mechanism that can quickly tell me, well, if you want to be at the letter C, then you will find it over there in that part of the file, right? So that I also don't need to start reading a huge file from the beginning all the way to the end, right? It's like I give you a CSV file with 1 billion records in it, and I ask you, well, tell me where the student with the first name starting with an S is, right? If I don't tell you anything else, your only option is going to be to read in from the top of the file, line by line by line by line by line, until the very end of the file, until you found all the students with the S's, right? So an idea that you could then say, well, if you're planning me, or you're planning to ask that style of question often, I'm first somewhere else going to write down in which positions are there students with the letter S, with the letter T, with the letter U, and so on, so that later I immediately know where I need to be without having to read line by line by line and checking and checking and checking all the time. That's what an index mechanism is. Of course, there is a whole lot of ingenuity that goes behind it, but now today we have tools available that can do this relatively well. What's the cost of it? Well, if you create indices, these things take up space as well, right? So you do need to have sufficient storage space, but typically, I mean, nowadays storage space is not that big of a burden anymore. What also helped a lot there is the availability in fast storage space, like on an old mechanical hard drive, right, with a spinning hard disk. It's way slower to move stuff from memory to storage than it is nowadays with an SSD available, with flash-based memory, with solid-state memory available. But then you actually have a way that you can work with data files as large as your storage capacity is, and without going fully distributed, right? So it's nice that we have this available today. Whether you use Dask or whether you use normal pandas, like I said, it doesn't look wildly different. This will crash if the CSV file is too large. This will not crash, right? It's not always perfect. There are some operations which are hard to set up in a way that allows it to swap data in and out, or that allows it to be run in a parallel setup. But today, this is not really an excuse anymore. And it's fun today because we see a whole lot of organizations that have jumped on the Hadoop wagon, and then later they adopted Spark. And Spark also helps to solve this, but also does way more. Spark also kind of makes the assumption that, well, you will also store your data in a distributed setup, and you will compute in a distributed setup. So you won't have just one machine, you do have multiple machines available. But maybe now we have kind of realized that we went a little bit overboard for many applied settings, not all. But it's, again, pretty fun how he went like through some kind of history in that sense as well. So again, here you see kind of the comparisons between Polars and between DuckDB. I already mentioned these. So yeah, many of these do also implement like stuff that they learned from Spark as well. So they implement indexing mechanisms, which can be very aggressive. Column-oriented data structures rather than row-oriented data structures, because column orientation typically matches better with the style of operations and queries that you want to do in analytics. And then ways to take a query that you want to run, an operation that you want to run on your data that typically consists of a couple of steps, and creating a directed acyclic computational graph from that, from which you can then say, well, if I can express my steps as a graph that does not contain cycles, that's basically what a DAG is. So on a very low level, what are the things that I need to do to kind of produce my end result? Well, from there, it's very easy to then say, this is a step I need to do first, and that can be done by one machine only, or by one core only. But then these two, they can be done by two machines in parallel. Right? They can run next to each other. And then, yeah, maybe some steps will have to wait until all of the previous things are finished, but the more I can do in parallel, the more operations I can execute in parallel, the better. And that's how you make these tools smart, right? How do I as efficiently utilize all of the computational power that I have available? All of the cores in my machine, or all of the machines that I have, right? And then the second step is, if I do need to load in data that comes from some storage layer, my hard drive, to the memory of these machines, well, how can I avoid doing this too many times, right? And how can I try to keep data in the memory of a machine for as much or as long as possible if I know that I will need to do something else with it later again, right? So this is more about, if I know then that this step will also need the same data elements, and you have already loaded it into the machine that is this step, well, then let's have the same machine do that step as well, because this avoids me that I have to load in the same data again, because it's already in memory. So there is a lot of cleverness involved in setting this up, cleverness that we will deal with at some level of abstraction. I'm not going into all the details, it's quite technical material. But from let's say a practitioner's point of view or a use case point of view, today we actually have good tools that can help us for that. If your main concern is volume, right? If your main concern is data elements that map very badly to tabular structures, like you really have images or video or text or audio or graphs, it's going to be a little bit more tricky, right? If you really have high speed data that you need to deal with, then there is also something to say for more special suited or more distributed environments, let's say. So we'll continue with this discussion on Spark later on. Now, first, before we do that, a bit of intermezzos. The first of which being kind of a little chat on these notebooks and labeling tools and file formats. But first, I see it's already 2:30, so we'll first go for a 15-minute break. So also for the notebook part, yeah, like I said, a bit of intermezzo of like a couple of additional aspects that are a bit specific to the world of data science in terms of tooling. Notebooks obviously being one of them, although it's older than data science or the field of data science itself. It actually comes more from the world of mathematics, with things such as SageMath and Mathematica, or even things like JOS from the 1960. Comes also from a style of what was called previously literate programming. Donald Knuth had some interesting things with that as well. But like nowadays, of course, everybody knows Jupyter, and which itself was a continuation of the IPython project. You can read a bit of the history here if you're interested in that. The idea or the switch from IPython, as it was called before, that's still why the extensions of the file names are .ipynb. Why that became Jupyter later is because they added support to utilize not just Python as a kernel or a language in a notebook, but also other languages. You can't mix different languages in the same notebook. There were initiatives that tried to do that, but again, from the moment you allow people to even mix languages in the same notebook, you can kind of feel that it becomes a bit of a mess. So that was maybe not the best idea. It's extremely popular. You know what it looks like. If you haven't used it, you should. You can use it in the web browser. They have like also IDEs have support for it nowadays. What's the benefit of it? The benefit is that you have an ongoing conversation with your programming language. Contrary to just, I will write the code and save it in a file and then run it, and then realize I've made a mistake and have to make some changes and run the whole thing again. Here you have like an open session, an open dialogue, typically then combined with a question-answer style of programming, where you organize your stuff in cells and you type the code that you want to see, you press run or execute and you get the result, but the session is still open. You can then continue to a next cell and again utilize the same variables and so on. Very often also support if you want to show a visualization, that this can end up in the same notebook, that this doesn't open in like a separate window. So you get like a kind of a living document that's being created on the fly, like a lab notebook as you would have it before with pen and paper, which is very suited if you're exploring things, if you're doing experimentation. It also comes with a couple of drawbacks. First of all, there are other alternatives other than Jupyter, although Jupyter is the most popular one. There were alternatives like Apache Zeppelin. Every time that there exists something outside of the Java ecosystem or the JVM ecosystem, they feel that they need to have their own thing as well. In the beginning, the claim was, okay, Zeppelin works a little bit better if you combine it or you utilize it together with Spark. Data scientists were so used to using Jupyter that none of them ended up using that, and it didn't really went anywhere. It's still also Jupyter that's the most popular one in this environment. Beaker is the one that wanted you to mix languages in the same notebook, but that also didn't really go anywhere. And then you have things such as Interact, that was like a first initiative to have Jupyter behave a bit more like a desktop app. But again, versions nowadays of Jupyter with Jupyter Lab, this is a little bit outdone or a little bit outfaced by that. And then you have languages or you have notebook environments for other languages as well, like Observable HQ utilizes or is built on top of the JavaScript ecosystem. And so again, this is pretty popular with people that are pretty versed in visualization. It's even more extreme than what you would get with Jupyter, because here cells that you add in afterwards in the notebook can influence cells that you added in earlier in the notebook. So this is even more of a reactive style of notebook programming, but you can see it's kind of a similar idea here. So that's why here in this notebook you can have stuff that's added in as the last cell, but still it influences things in the cell previously. So it's like it's kind of fully interconnected. Again, a little bit more difficult to wrap your head around. Pluto is also a same style reactive notebook, but for Julia. They used to have something like this. So I did say, okay, I have n equals 3, but then here I change my mind, right? And then I can change this cell, but it immediately influences the previous cell as well. Jupyter is more of a bit of a linear style of execution. You execute cell by cell, and cells that you execute cannot influence the execution of cells that you executed, or the result of cells that you executed previously. In any case, it's easy to use. You can make dynamic reports with it. You can even make presentations with it. You can make them interactive. People have even written whole books with Jupyter. So in that sense, it's a very widely available or widely extensible platform. Companies such as Netflix, they also utilize notebooks directly to put them into production and to execute them and to schedule them as if they were normal Python scripts. And of course, that's not so difficult to do, because at the end of the day, they contain normal Python code. The only kind of gotcha, if you want to do this, is that obviously then you will need to make sure that you can execute your notebook every first of the month, for instance, from top to bottom, right? Then you do have a linear execution from top to bottom. If I look at the notebooks that students sometimes show me, they have like 20 pages in one Jupyter file, and then they go, well, first I did this, but then I went to the bottom, but then I re-executed this, and I went down again, and I went to the top again, and I changed something here. That's obviously not going to work to be executed multiple times. And that's the biggest drawback with them, is that they are very quick to iterate on ideas. But then at some point you want to settle down on a pipeline that works, and then you will often find that the notebook that you have in front of you is quite messy. It's the result of an experimentative process, of an iterative process, but not something that's ready to be placed in production. Now, there is an easy way out of that. The easy way is that you force your data scientists and tell them, look, you can experiment, that's all fine, but what you need to deliver as the end artifacts is a collection of even notebooks, why not, but notebooks that have been cleaned, where you have a separate notebook for each step: data loading, data pre-processing, model retraining, predicting or scoring, in a way which is executable from top to bottom, and in a way which is idempotent, so that I can execute it multiple times or every first of the month or something like that. So this already reveals a bit the style of working between data scientists when they work during the development of their model, versus, okay, now my model is finished, how do we now put this into production and we make this clean, right? Because we also know that from time to time we will want to retrain our model. Can we next month or next year, can we redo all of the steps that you did here to automatically retrain a new version of this model using the latest state of the data as it is in our database, right? And that's typically a way harder question than, oh no, I just have a notebook here and everything is mixed up, but there is a model somewhere, right? I've saved it as a pickle file or something like that. So this requires a bit more governance to do that correctly. So there are a couple of issues with them. The execution can be difficult. Writing modular code, this is also something that you see frequently, is that people have their favorite snippets of code that they add in at the top of every notebook that they ever write. And they copy paste it all over the place. Yeah, at some point, if you feel that you're reutilizing the same pieces of code everywhere, then you should think about, let's create like a Python package out of that, or let's create a module at least out of that, rather than kind of copy pasting it in every notebook that we have. Version control can be a bit problematic because this is kind of a JSON schema as a file format, which can be pretty messy, but there exist ways to avoid that. So none of these are really kind of harsh criticisms. All of these can be avoided, but it does require a bit of governance on top of that, a bit of management on top of that. Otherwise, you get like Wild West style of coding, which just leads you with a bunch of disgusting notebooks that no one can understand after 2 weeks anymore. So there have been like very harsh criticisms by, here you can see a couple of them. This was a presentation that was given a couple of years ago. I don't think that most people would agree with all of the statements that have been made or that are made here. There are some things in here that are correct. Can be difficult for beginners. Yeah, sure, maybe. Out of order execution, yeah, for certain that can happen. Um, Make it easy to teach poorly, make it hard to teach well. I'm not sure. I think notebooks can be a great teaching tool. So I don't think that that's really been proven. I think quite the opposite have been proven on that. Reproducibility, I don't think has anything to do with the notebook platform as a platform itself. But people have been sometimes harsh on this as well. But I think by now, the fact that they have been so widely adopted and utilized, and even complete products like Google Colab or Amazon or Azure ML Studio have been built around this, shows how widespread that they have become. So in this case, for instance, the only thing that Microsoft does here is they offer a hosted Jupyter installation with already a whole bunch of packages pre-installed that you can utilize, or a whole bunch of libraries pre-installed that you can utilize. But it's based on the exact same technology there. So everybody has realized that the best data science environment that you can offer to someone is to say, well, here you have Python, you have Jupyter, you have the possibility to pip install stuff that you need, and you can get started basically. Put that on a beefy machine, and you have your data science environment. And the issues that we just discussed can be solved. Even like writing clean code, there exist linters such as PyNBLint or NBQA that can format your code, that can lint your code, that can run checks on your code to make sure that you get clean production-ready notebooks, just as you would get normal clean production-ready Python code as well. But it is certainly true that there is a difference in the way how notebooks are written during the development of something, when it's a lot of small, quick checks, a lot of experimentation, and during going towards production of something. And that is certainly the case, but you could say the same thing for normal code as well to some degree. Now, that being said, some people also like utilizing the more traditional integrated development environments. Our people are a big fan of RStudio still, which can also run in a web environment. Some people stick with PyCharm of JetBrains, which typically gives you better debugging possibilities than what you would get from Jupyter. So that's also certainly a critique that you could raise to that. JupyterLab is kind of the newer style of interface that Jupyter offers, where they say, well, before you had to have every notebook open in a separate browser tab, but maybe you like to have something like this instead, which looks a bit more like RStudio, where in one browser window, you can have multiple like windows in the same screen. Maybe something showing your files, maybe a terminal open, and maybe a couple of notebooks open there as well. And even today, if you install Visual Studio Code, and you double-click an IPyNB file, it can directly open it up into Visual Studio Code as well, and you can execute it just in the same way as you would do with Jupyter. Maybe with a couple of bit more configuration steps here and there, but it goes to show that this idea of this interactivity with your programming language, that this is something that's been widely adopted by also the IDE vendors. This is Dataspell, which is JetBrains' IDE specifically geared for data science, which is also not that bad. So you have a lot of choices, but like notebooks are really the lingua franca there in terms of interchange of code in data science. So this is then what you get in terms of Python and R. Yeah, then the last question is basically, where do we have this run? Install it on our local machine or utilize something like Google Colab or Kaggle kernels, somewhere where this is hosted for me. And then no matter where you set up your platform, you can run this technology stack, basically. Another extra tidbit is about labeling. Yeah, we often assume when we talk about toy data sets or we talk about academia, that it's easy to get data, and that's true. It is easy to get data. What's typically hard in real life is getting labeled data, right? Because there is kind of a hidden element here at play, and the hidden element is, if we would have already had something that historically labels all this data for me, then why do I need to build a predictive model to begin with? Right? Because then I had something that was labeling this data. I already said this before, then basically the only reasons why you still need a model might be because you believe that the labeling is incomplete, or is sometimes wrong, or is noisy, but then are those labels going to be helpful for your model? Then why do supervised modeling? Or maybe you want to automate the labeling. Maybe the labeling is very costly and you can only label a part of your instances, but not all of them, and you want to automate that process. That's typically a reason where you see predictive models being deployed. is because the labels are either based on outdated style of models, human expertise or rule-based systems, or because it's hard to execute the labeling process itself because it involves human effort and you want to replace that human effort with something that's more machine-driven. And then basically the supervised model acts as a way to capture all of that tacit knowledge that is present in those underlying processes there, right? So it's a bit strange, but in real life it can be quite tricky to get sufficient labeled data. So it's not uncommon that a whole piece of the work that you will have to do in real life settings will be exactly to label your data yourself as well. And you can imagine, of course, with tabular data, it can be quite reasonable. You could have some people label that for you. It becomes more complicated if you go into time series data or if you go into image-based data. Depends also on the style of images. Is it just saying this image contains a cat or a dog? Then it's just picking a button. If it's about, well, please show me exactly where the rooftops are in this image, well, if you're a human and you need to do that, I mean, you can already feel that this would be a bit more work to do this with, right? Now, the open, again, another kind of secret of the industry, if you look at companies such as OpenAI and so on, is that they spend enormous amounts of budget paying people in India, China, and so on to do nothing but label images, text, and so on. There was even the story a week or so ago, or a couple of weeks, about these grocery shops of Amazon in the US, where you could just walk out and there was a smart camera that was looking at what you purchased and then immediately sent you your bill. Right? Great experience. You just pick your stuff, you walk out, and you're being charged automatically. That there was no AI model behind that, but that was basically humans following all of these cameras. And of course, you know what the plan is. Their plan is to create labeled data. First, have the humans do it, and then at some point, we will train a model on all of these video feeds that we now have and all of these labels that these humans have now made, right? But they didn't tell that, right? Everybody assumed that this was some kind of AI model that they already had. For companies such as these, very often the first easy step before you have an AI model is, let's just pay a bunch of humans minimum wage. Right? So there is kind of a bit of some strange effects at play here, but don't think that if you read stories like these that it's always so easy. There is a lot of labeling involved. Also, to train ChatGPT, for instance, enormous amounts of data scraping and labeling and cleaning efforts involved with that. So yeah, you can hire manual labelers. What you will typically find in tools that try to improve or speed up this process a little bit, well, yeah, of course, if you need to label this, you want to label as least instances as possible, right? So in a sense, the quicker you can have a basic version of a model up and running that can already give guidance to label the next image, for instance, the better, right? So that's what many of these tools will do. They will do that by using a pre-trained model and then trying to fine-tune that or retraining a model on the fly as you're labeling, right? Maybe, okay, you have a pre-trained model and it was not exactly tuned to find rooftops, but maybe something similar. Maybe it already does a bit of a job there and you just need to make small adjustments, right? Another thing that they will typically combine is an active learning approach where we try to, based on some heuristic, and you have all sorts of them, to basically see, okay, what is the most informative next instance that we can ask the user to label for us? If it's one where the model is already or would already very likely predict the right thing, then maybe we don't need to ask that one next, right? It's better that we ask an image where the model is still confused or which is still difficult for the model. What it means to be difficult or confused, you can have different interpretations of that, right? Some common ones are, okay, images for which, let's say you do binary classification, images that are close to the decision boundary, 0.5 as a probability. Those make sense to be asked first, but we have already seen that probability and certainty is not really the same thing. What about images or instances that lie far away from the ones that you have labeled so far? Now, that's also interesting. Images where if we look at the prediction that your model so far gives me, and we compare it to the prediction of a KNN model with the 10 nearest neighbors, the images for which those two predictions differ the most, we will ask next, right? So you can come up with a whole bunch of heuristics to kind of rank or sort the images in terms of, or other instances, in terms of interestingness, in terms of what should we ask next to the end user to label for me. So that's typically what these tools will try to do. I've used quite a lot of these tools, including some commercial ones. Also, from time to time, you will find that sometimes the best way to go about it is to implement your own thing just from scratch. Just write something with an ugly web page, using something like Flask or a bit of JavaScript on top of it. Depending on what you want to do and the speed that you want to label with, not all of these tools are as suited. But you do have a whole lot of them that you can play around with and that you can test out. And on this website, a whole lot of them are listed. As an aside, there are also companies that have proposed things such as HumanLearn, which is a bit strange because you could say, so the idea here is well, we will show the data like this, ignore the colors of the dots for an instance, but what we will ask the human to do is draw like polygons and label manually like this, right? The question with this is, okay, but we know if you do this in 2 dimensions, that yes, this might be possible. You could even like maybe visualize the color in terms of target or something, but then aren't you just replicating a very simple linear model in some way by then contrasting it with pairwise feature sets? And I mean, if the data is this easy to be labeled on, then yeah, I mean, any simple model is going to do a good job probably, right? You could also say, well, no, this is the result of first doing t-SNE or PCA and then showing the most 2 important components, but then which human is going to understand that and how are they going to draw polygons on top of them? So again, strange idea, because this makes me wonder, okay, either the setting is so simple that indeed you don't need a model to begin with anyway. I mean, yes, your human can just make the model, and the model is then basically an Excel function, but okay, fine, that's your model then, right? It's also a model. Or it's so complicated, but then you will have no way for a human to do this, right? Now, companies like this is another one, Snorkel, they say, well, we will allow also humans to kind of define labels, but not by drawing it, but by basically writing down rules. If age is higher than this, and income is lower than that, and this is higher than this, and this is lower than that, and so on, then yes, or then no. And they say it's still valuable to do this, because it's not necessarily the case that this data set is very simple, because what you will find is that, first of all, humans will not be able to label the complete space of instances that you have. If you give me a bunch of rules, and I apply them on my instances, I will not be able to label everybody, right? Because your rules might not be fully covering. What I might also find is that in the way how you define your rules, is that I might have instances that fall both into the selection of multiple rules, maybe even contradicting ones, where according to some I am a yes, and according to another rule, I would be a no, right? And they say, still we can utilize this because it's a nice name that they gave. They say, well, what the human labeler then does is they provide a form of accidental regularization by doing this. By not having full coverage and by having overlap, you get a regularizing effect which can then still help a model that you build on top of that. Yeah. Maybe. I'm not fully convinced, to be honest. Maybe there is something to say, but it's kind of the same story that you heard a lot of in recent past about synthetic data. If we don't have enough data, we will use synthetic data. Yes, again, but this data is going to be generated from some distribution that you define. Same here. Yeah, you can use this as a generative model, fine, but then basically, once you have a generative model, then yeah, for sure, you can learn another model on top of that. But then let's be honest, and that generative model is your model, right? So not 100% convinced, but again, this is how consultants make money, right? By coming up with things like this. And of course, to companies, it sounds very nice, right? Oh, no, you can have your human still labeled, so then they still feel important and human in the loop and so on and so on. Okay, fine. File formats. This is a little bit about how do we save our data, but also maybe how do we save our models. So first about data, there everybody knows about CSV-based formats, textual-based formats, but you could wonder, well, are there other maybe non-textual formats as well, right? And do they make a difference in terms of how fast is it to write them? How fast is it to read them in? Do they have metadata? Or they column or row based. If you look at the CSV file and you go from top to bottom, you see that it's row 1, row 2, row 3, row 4. Maybe you have file formats where it's column 1, column 2, column 3, column 4 instead. Would one be better than the other? Is it easy to modify the schema? Meaning that, let's say I give you a CSV file, and now I want to add in a new column and stick it between two existing columns, right? Or I want to reorder columns. I will have to go through this whole file to execute this reordering. There is not like a smaller operations that I can add in the beginning of that file and say, hey, if you read me, read the columns not in this order, but consider them to be switched around. Right? It doesn't have any additional meta information in that file. It's just a bunch of textual rows. That's it. So probably there are other ways as well. So the benefit of textual formats is that they are human readable. You can open them up with Excel or Notepad or whatever, and you can kind of understand them. But they can be very bulky and not very efficient to query without reading in that whole structure into memory first. Playing with that schema or that metadata is not so easy. Applying compression typically is then applied on the whole file rather than on specific contents. But it's still, of course, very commonly used because humans are so used to it and we know that we can just open it up. Still, a CSV file does not really have a standard in the sense that whether it uses commas or semicolons, whether it uses double quotes or single quotes or triple quotes, whether it escapes with backslash or with double quotes, and so on and so on. Take your pick, right? So if you send me a file and I'm a tool that needs to read this in, what do I need to do? A lot of guessing, basically. Is this first row, is this a header? Or is the first row immediately data? For all of the columns that you have here, what's the type of them? No idea. So the only thing that I can do, and that pandas and so on end up doing, is let me look at the first 100 rows. Yep, all looks a little bit like a date, probably is going to be a date. Right? Yep, looks a bit like a number, so probably is going to be like a number, and so on. So you don't even have like a description for each column, like saying what type is this, which is also why like very old formats like ARFF were at some point more popular because at least they contained a description of what type everything is. Broken CSV files with a new line in them, or comma, 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 or different number of columns per line. So a tool that reads in a CSV file needs to be able to deal with a whole lot of edge cases in order to handle this file format. And if you're unlucky and you send something like this and someone opens it in Excel, I think with later versions it's probably patched out, they get a pop-up and they press yes, then this thing can make calls to the web as well, which is not a problem of CSV, that's more a problem of Excel, to be honestly. But also in terms of safety, there is maybe something to say for them. If you open it with Spark, this is not going to happen, obviously. Now, there are other or alternative mechanisms as well, like sequence files, which is basically just serialized Java objects. Older versions of Hadoop were built on top of Java. They need to transfer data from one machine to another. So how do we store this? Well, let's just take the object as it is in Java and dump it out, mainly meant for transfer from machine to machine, not so much between humans. Or C was then an evolution of, or C files, which themselves were an evolution of these sequence files. A little bit of a change because it's stored in a columnar style format. It had some indexing support, also not so popular in the recent years anymore. This was also something that was used more in the Hadoop world. Avo is a newer one. This one is relatively widely used. So this is also serialization format for data, binary, not textual, row-based, has a schema in the file, supports schema evolution, including adding, renaming, and deletion of columns, can apply compression on the record level. Not uncommon nowadays to store data, especially if you are writing a lot of data, because it's relatively fast to write data out. Another new one is Parquet, and you could even say even more popular. It's column-oriented, and typically column-oriented formats are better suited for analytical use cases. Supports efficient compression, has schema support, and pretty good support for schema evolution. You can add columns to the end of the file, not just put them anywhere that you want, but you could say that's maybe not that much of a drawback. Parquet files have become quite popular nowadays as a storage format. You might not have seen them, or you might still be utilized more to CSV files, but it's quite likely that if you would work as a data scientist that you will encounter them at some point. You will just not be able to open it up with Notepad and see what's in there. You will have to do, like in Pandas, read Parquet or something like that, and then look at it. Some cases, data is also stored as a SQLite file. It's also quite common. From there, the benefit is that you can then immediately utilize SQLite tools to perform querying on top of that. You also see, and this is exactly what DuckDB and ClickHouse do, they also come up with their tables in a file storage format, but typically SQLite is row-oriented. They typically do it in a column-oriented manner, which again makes it a bit better suited for analytical purposes. In SQLite, typically what you would find is that you would also have to add in a lot of indexes for it to do fast queries. With DuckDB and ClickHouse, typically out of the box, it already gives you good support for at least analytical style of queries. If you're ever wondering what makes an analytical style of query different from a more operational style of query, in analytics, we typically want to do complicated operations in one table because we're used to working with one data frame. So we want to do a sorting and a filtering and then do an aggregation and then do a group by and whatever in one table, versus in an operational setting, you typically do simpler style of queries, but you join multiple tables together. So you have that inner join and outer join and so on going on, and there a row-oriented mechanism tends to be a bit more better suited for that. HDF5 is even more complex. It's a whole file system inside of a file with a very complicated specification with support for all sorts of data types. So this is basically, well, all the contents that you have on your normal hard drive, including directory structure and file names and different files and permissions and different types of files, but all of this stored into one file. It's basically like a whole file system inside of the contents of a file. So not very popular, except that at some point in time, this was the most popular choice to store, for some reason, the weights of a trained deep learning model. So it's still not that uncommon to find a .h5 file with the weights of a pre-trained model. Nowadays, there are better alternatives for that. We have things such as ONIX, and we have things such as Safe Tensors, which is being utilized a lot. But this is still, from time to time, you will encounter this format as well. Kudu is a storage system for tables of structured data. So again, it's an alternative if you contrast it to SQLite and to DuckDB and to ClickHouse. This is something that, again, the Apache ecosystem came up with. So if you utilize database technology on top of Hadoop or on top of Spark, then sometimes you will encounter this one, but a bit less popular. Apache Arrow then tries to solve the solution of, okay, you have all of these tools, they have all of their own representation of data, but it also means that if you want to then go from one tool to another tool, your only choice is basically then to take what's in memory, write that out in the form of a CSV file or whatever, right? And then use your other tool to read that back in. So that's a bit of a wasted step. It would be way nicer if we could read it as one specific representation, right? Because it's not because your data on disk is represented as, let's say, a CSV file, that once you have read that CSV file into Pandas and you would look in your computer's memory what that data looks like, that will look different than if you do the same thing in R and you go look in your computer's memory, right? So that's the internal representation of the data. So that's why in one tool, even if you would allow both of them to look in the same space of your memory, that one tool is not going to understand what another tool has put there because they differ in the way how they represent data internally. So that's what Arrow wanted to solve. They said, well, for data frame style structures, let's come up with an efficient representation that then every tool can utilize, right? And also the interchange will then be much easier. This is actually one of the things that helped a lot in the later versions of Pandas, is that they switched to an arrow-based representation, which also subsequently made a lot of operations way faster in Pandas as well. Now, it's not so common that you will face the problem of, now I want to convert something from Spark to Pandas to Impala, and they can read from the same memory, right? It's nice that you can read in from your base files and that you have a good representation interchanging directly in memory. You don't see it that often. So what then happened next is people said, okay, this is helpful. The representation at least is not bad. But now that we have a representation in memory anyway, what is then stopping us from also using that as a long-term storage format? Take the contents in memory and write them to a file, right? Because then you also have a storage format. And that's the idea that Feather had. Feather said, well, fine, we have data, we can represent it in Arrow, it's in memory, let's take the contents and dump them out to a file, ta-da, new file, storage format. Arrow said, yeah, but we are not meant to be utilized in this way because we are still changing a lot. So something that you dump out now, maybe in a few months from now, you will not be able to read that back in because we have tuned the representation again a little bit. Eventually stable enough. And because Arrow itself is actually a good representational format, it's also not a bad file storage format either. So also Feather files is something that you see more and more of these days, right? So you can now, and again, notwithstanding the tool that you utilize, you will have a library that can read them in. The takeaway from all of this is be prepared to see more formats than just CSV files alone. And in terms of popularity, Avro, Parquet, and Feather, these are the main formats today, in fact. And you will see that organizations that have gone like a little bit beyond the CSV style or the Excel file, God forbid, style of storing data, that these are the ones that they are adopting, right? Yes, you can open Excel files with Python, but I mean, I wouldn't recommend it as a long form or a long-term storage solution in any form. Another thing that you will encounter later on, and which this is not like a full ML ops style, of course, obviously, but like another thing that you will have to deal with at some point in time is packaging and package managers, right? Both in the R world, but also especially in Python, you will see that from time to time. So package manager is a piece of software that allows you to easily install and keep up to date all of these add-on libraries that we just discussed. I need a place to download NumPy and Matplotlib and scikit-learn from, right? So this is what a package manager will do. Typically with a bit of metadata so that it knows, you want to install scikit-learn, you don't have NumPy yet, so then I also need to install NumPy for you to utilize scikit-learn, right? This is then typically combined with a virtual environment. Because then the next question is, okay, for this project, I'm using scikit-learn version 23 point this point that, I'm using NumPy version this, I'm using PyTorch version this, and I may be even using Python version 3.8 or whatever, or 3.12. I want this thing to run for a long time, right? So I would like to contain all of these packages and freeze them in one environment, and then be able to create another similar environment for another project where maybe I use, again, the latest versions of these things, but then I can keep that other project stuck in the environment that it is in, or frozen in that specific environment. Why? Well, because I know that these packages, they will change over time. You could say, well, why not just keep them all up to date? Because tomorrow, the package managers or maintainers of PyTorch are going to make a breaking change, and my code will not run anymore, right? So I want to avoid that from happening. So I want a frozen environment. It also makes sure that I can tell you about my environment, and I can give my code to you and tell you these are the exact versions that you need to install, and then this code can work. So it's also a way to make this reproducible. Now, in Python and in R comes with its own package manager. That's what it does if you call install.packages. Virtual environments, you can utilize Packrat for that, which is our kinds of own virtual environment manager, or you can use Conda as well. Conda is a general purpose package manager and virtual environment provider that tries to step beyond Python, but virtualize it on the level of like the full binary environment. So that's why it also works with R. Python has a lot of package managers. A very common one is pip, which is included with Python 3 by default. It had previous ones as well, setup tools-based ones. Python also has a lot of virtual environments, virtualenv, venv. You can also use Conda, again, which is kind of both a package manager and a virtual environment manager in one. So you can also use that to set up your Python environments and in there then install packages using Conda or using pip. This has a couple of side effects. And the side effects of this are that there is a lot of interplay between people saying, well, the best way today to work in Python is you should use pip and venv. And don't bother with Conda because it can be slow sometimes. And Conda people say, yeah, but use Mamba instead because this is faster and it just works in the same way. Or you use Conda, but inside of Conda, it's fine that you use pip. Right? So again, here with Python, the issue is not that we have too few solutions, but sometimes we have too many solutions for this. And people can't stop because an even newer approach is Poetry. And this tries to offer you all the tools you might need to manage your projects in a deterministic way. Builds on top of pip, is also oftentimes combined with Po the Poet, which is a task runner that works well with it. And can also help you to set up like virtual environments per project. If you want to see a very nice, or maybe an extreme case, sometimes then to virtualize or to isolate even further, what Poetry and pip will do is they will isolate Python and all the libraries that you need. But there may be things outside of Python that you're using as well, like your operating system. So if you want to also isolate that and freeze that and keep that into a specific environment, then it's not uncommon to then still combine this with containerization tools such as Docker. And Docker, they isolate on the level of a whole operating system. Right? So then you have not just your Python version and the libraries around it, but you also have like Linux, Ubuntu version this, and with maybe these packages in Ubuntu that we need, and then with Python, and then we use Poetry to install all the pip packages. Again, benefits, reproducibility is pretty easy, right? Every time you deploy something to GitHub or whatever, it can be automatically redeployed, and everybody knows exactly in which environment that this code needs to run. For a nice example, you can check out this GitHub repository that gives like a very clean starting point. Let's say today you say, okay, I would like to develop a new Python package, the new XGBoost. And it's like a clean way that I can offer this to the outside world, right? So that they can easily reproduce this and set this up. This offers a good starting point. The drawback sometimes that you see with this is, well, eventually you will like to update libraries that you're using. Because, well, if it's code that's being used up until today, and we know that from time to time we will have to maintain a model, for instance, well, we might also just maybe check what happens if I now also update scikit-learn. It's probably still going to work. It's not going to break my code in most cases, right? And probably they will have made it better and faster, so I would actually benefit from updating. The expectation with all of these tools is that some maintainer or someone will from time to time go back into that virtual environment and do these updates, check if it still works, and then says, okay, it still works, now we can update the environment and we can work on the latest version of scikit-learn. Of course, that never happens. People just have that code run on a version of all of these libraries from 5 years ago, maybe even with security exploits in them, right? So with isolation and virtualization also comes, yeah, this is something that a lot of young consultants and juniors, they love this a lot, like, oh, everything is so reproducible and we can isolate everything. Yeah, true, but it's not because you isolated everything that it's necessarily all maintained automatically, right? No, you have just isolated it. It will break less easily, but it will become outdated just the same if you don't update it manually or don't maintain it manually. That's still something that you will have to do, right? Also something in terms of, well, if you work with a team on code, you will want to use a versioning system, and Dropbox is not a versioning system, right? If you work with 2 people on the same file, you get conflicts, and you maybe want to create branches of code and so on. So this is what a versioning system wants to or provides to you. The most popular one today is Git, because this is the one originally developed by Linus Torvalds for the Linux kernel, but now exists. That's what GitHub uses. To host repositories. It uses Git as software and it offers this to the world. Like everybody can host a repository there, but you basically use Gitdem as your version manager. It's not the easiest to learn, especially for like complete newcomers. Like wrapping your head around all Git operations can be quite daunting. An easy tip, to be honest, is don't feel afraid. Install GitHub Desktop, which is basically like a graphical user interface to push your code and pull your code and commit your changes. It's pretty much an easy starting point to start working with it. And then later you can learn the command line tools to utilize Git and to utilize GitHub. But also quite likely that you will have to work with this at some point. Recruiters, more and more, they will expect that if you apply as a data scientist, that you put your GitHub repositories on your CV, where you show these are projects that I have done, or these are experiments that I've done, right? Have a look, see what I developed before. So it can be quite worthwhile, even if you're not like producing stuff that's production ready or industrial or whatever, just small experiments, like put a small article somewhere on there, put a small piece of code somewhere on there. This can be quite helpful. Like for the assignments, if you felt that you did a good job, by all means, put them on your GitHub profile and utilize them if you go to apply somewhere. This can be a good idea because recruiters do check this more and more. Then, to end up with, model deployment. Yeah, I already said that this doesn't, so evaluation of models doesn't stop at deployment. I think I already at some point or might have mentioned an already pretty old paper, but that really describes this very well, hidden technical depth in machine learning systems. It's a paper that made very good statements. Statements like, if you look at real-world machine learning systems, only a small fraction of that code is actual ML-related code. There is a lot of boilerplate in there as well. So there is surrounding infrastructure, there is surrounding processes to support them, and there is a whole lot of potential weaknesses and dependencies and complexity and monitoring that makes this difficult in practice. So people think, well, it's kind of visually, it always looks like this. You have kind of a development cycle where you take in data and you write training code as like a programmer, and you maybe iterate a couple of times through here. From there ultimately comes a final model, and then you will make a choice how to deploy that model. Maybe as you will embed it in a mobile app, or this will be exposed through an API, or this will be something that runs every week on a server somewhere automatically, and that's how the end users will be exposed to that model. But in reality, of course, it's more difficult than that. It starts, for instance, with data. It's not uncommon that during development, you apply steps to develop your model, which leads to the creation of features for which it might not be a given or as easy to still get access to those features when your model will actually be utilized. Remember, the goal of a predictive model at the end is to make predictions. So it is very, it happens quite often that during the development that even stakeholders or business people around you will tell you, I have a data set here somewhere that my team has, it's in an Excel file. Couldn't you try to use this because the information there might help your model? The answer to that should then be, yes, you're right, it might help the model. I can actually check that even for you, but do keep in mind that if it helps the model and we want to utilize that, we can't then just continue to stick to this one-time Excel file that you then gave me, because the features that I extracted from there, they will need to continue to come to me as my model is being utilized and as my model is making predictions. So I will need to be able to re-execute all the same pre-processing steps. You will need to guarantee that you can keep this information now up to date, because I will continue to utilize it. So we need to come up with a structured process to make that information part of a joint data layer, a storage layer, a feature store, if you will, right? Otherwise, if this is just like one data set that you found in 2023, no, sorry, right? If you can't guarantee that you can give it to me in 2024 again, I know by definition that it's going to be outdated very quickly, right? So you can have all sorts of nice ideas of data to utilize, right? And this is kind of the mistake that stakeholders make in a lot of cases. Say, oh, we have all this data, why can't you look on Facebook and look on there and look on here? Yeah, we can look everywhere. The problem is not looking everywhere. The problem is you need to productionize that. Your model will need it then going forward, right? Same for the deployment context. How do you keep model changes in sync with application changes around it, for instance? The fact that the data science environment, where people are used to working with Jupyter and so on, can be totally different from the IT environment, where people expect to deploy .NET artifacts, for instance, and they use a completely different packaging system than what you're used to when you're using Conda or whatever. can also create friction between data science and IT teams there. Governance, I already mentioned this. Training code, do you give me a bunch of ugly notebook files, or is this well-documented training code? How do we handle collaboration, versioning? Can it be easily reproduced? Is this something that can be re-executed and deployed? There is a difference between experimentation and creating production-ready code there. How do we deploy the model? Do we use a common platform? Everybody needs to use Python. Do we even maybe use a common algorithm? Everybody needs to use XGBoost. Do we use Docker? Do we use virtual machines? Do we have versioning support for models? Can we switch? Can we go back to an earlier version of a model, for instance, if we see that a newer version does not work as well? Can the output of one model be easily used in another model, right? Can you give me a list of existing models, and can I easily utilize their outputs as features in another model that I want to build? You don't typically think about that, but very often what ends up happening is that organizations have 100 models, and if you would make a correlation plot between their predictions on the same instances, that they all tend to do kind of the same thing anyway, right? Because you always want to predict kind of the profitability or the viability or the eagerness of a customer or something like that. Is metadata available about models? Do we monitor inputs? Have my features changed back or compared to the time when I trained my model? Is the output distribution of my model changing over time? Is usage changing over time? Maybe people are less frequently calling my model API. Is it because they are losing trust, because they're getting unhappy with it? Do we have statistics on that? Do we have metrics on that? Or errors reported or errors logged? Do we see new values for or levels for categorical features that we didn't see during training? Do we see missing values that we didn't see during training? Can we handle that? How do we handle that? So in software development or in software engineering, we do have a lot of things that we can reutilize already. CI/CD, continuous development, continuous integration. We can run some tests. But you could say that in machine learning and in data science, it becomes even more complicated because of all the ML-specific intricacies that come up here or that show up here, that have to do more with the performance of the model as a model rather than the model being a software artifact. Also, even although it also is a software artifact. So people have been writing quite a whole bunch on that already, with statements such as machine learning models degrade silently. They will continue to predict. They will give you a number between 0 and 1. They will not suddenly say, I want to stop predicting because I'm too old. So they will happily continue to hallucinate and give predictions or whatever. If you don't monitor on that, you will get stuck or you will get tripped up by that. In stark contrast to software engineering, data science does not have a well-defined, fully automated process to get into production quickly. And that's even quite optimistic of a statement, because even in software engineering, budgets and time that is required to have something realized or to finish a project is typically underestimated, and it turns out to be a much higher burden than people think that it's going to be. In ML, that's even worse in many cases. Especially if it's the first time that you need to work with a new piece of data that you haven't worked with before, make an overestimation, because this will take way longer than you think that it will take, right? This is frustrating for managers, because then they say, well, why is it so hard to estimate how long that a machine learning project is going to take? Because of what we discussed also in the first course, this cycle where you have these loopbacks. Now, companies have been trying to improve this, and you have companies focusing more on the developer side of things, which is easy because developers, you have them play in a Jupyter notebook, you add some versioning and collaboration, and you give them lots of charts to do hyperparameter tuning and so on, and then they're happy. More the monitoring and the aftercare support has been a little bit more difficult. There have been some companies that came into the space, but it's also not uncommon here, and this again is a sign for companies, and especially these large engineering-driven companies. You see the names here, Uber, Spotify, Facebook, Netflix, to go, we should develop something in-house because we feel all of these problems and there isn't like an all-in-one solution for this. So imagine the IT capability that your organization should have in order to execute this correctly. It's not an easy task, right? And again, this is why so many of these projects do not get a positive return on investment, because they start with very high expectations, they're very overblown, but then there is no kind of governance in terms of how to implement this. I've listed some principles here, some tips on that, or some ideas on that that you can read through. Basically, yeah, these are things easier said than done. Yeah, it's about data management. Some problems here: model development data sources are typically dispersed and tangled, hard to keep track of the data used during a model's construction. Definitions are not clear or unavailable. What do you do with that? Well, data quality initiatives, data management initiatives. Don't play the role of a data architect and make a pyramid, right? I have an allergy for that. These pyramids are at the bottom, we have the raw layer, and then in the middle, we have the process layer, and then at the top, we have the final layer. Rubbish. Bullshit. What it means for data to be raw or final is completely dependent on the context. Right? The only reason why architects like to do that is because then they are the pharaoh who has the ownership of the whole pyramid, and they decide who can get access to the final layer, but never the raw layer. Right? That's only us. That's politics that you then get into. Of course, it happens a lot, right? And the larger the organization, the more that it happens, but that doesn't work. What does work is the realization that data is more like a directed acyclic graph, where you should be able to set up an infrastructure which makes it possible to combine data elements in an easy way together, and to ingest new data elements in a way which is reproducible and structured, and to also consider models and their outputs also to be data elements that can be reutilized by other models or by other artifacts. Not easy to set up, obviously. Train-run integration, reproducibility, and testing, already mentioned. Yeah, make sure that you aim for a reproducible pipeline. Make sure that you can automatically retrain models, that you can contrast their performance to earlier versions, that you can easily deploy or roll back versions of models. Implement monitoring, implement logging. There is a paper called What's Your ML Test Score that has a whole bunch of metrics that you can keep track of to see how well or how much is my model changing, or how much is my data changing compared to back when I trained this model, right? Do new missing values occur, stuff like that. Monitor it, right? It's not that hard, you just need to, or it is pretty hard, but I mean, content-wise, it's not that hard. The hard part is setting it all up, obviously. Already mentioned this before, there are companies that have jumped on this, and so this is the whole MLOps stuff, and that's why you see, the claims have been changing. Before, it used to be more about how can we have data scientists work together, and in an efficient way, and to do experiments, and so on. That has shifted. In the operations phase, it's more about how can we act on bias? How can we maintain data integrity? How can we benchmark changes? How can we detect concept drift? It's a different style of questioning that has popped up. And this comes from the fact that now organizations have realized, this development is okay. We just stick a bunch of PhDs in a room and they can have fun, and they will deliver me some final model. But then what happens afterwards is way more difficult, right? Then I have IT people standing at my door and complaining, right? So it's about this. Runtime patterns, how do models run? Do I go for an API style setup, or do I go for something that runs on a mainframe every month? You also have different architectural patterns that pop up there, which can also make changes in the way how you set up this whole thing. Isolated runtime environments are pretty popular, so the virtual environments, but also things such as Docker. You could even go a step further, and again, this is how you make money as a data engineer, right? Because then you have Docker, but you want to scale automatically. You have the same image in Docker, but now I have a lot of requests on my website. Now I want to spin up 100 machines very quickly, right? And now I have no requests, so I want to spin them down. So I need some orchestration around all of these containers, and some load balancing, and some automatic scaling. That's Kubernetes, right? The next level is, well, I don't want to do that myself. I will buy that from Microsoft or Amazon or Google, right? And because they have the infrastructure available. It's still the same technology beneath it, but then at least I'm using their infrastructure, right? Again, there is something such as going too far with this, right? Not every problem that you have requires hammers that are too large to solve them. So there is a trade-off between allowing flexibility also and allowing for robustness. That's also something that is sometimes forgotten. Sometimes governance initiatives that then go too far, they take away so much room for experimentation that also not a lot of innovation happens anymore in the data science team. And then you just see that it is kind of a model factory where they just use the same model algorithm, they use the same features, they just press click, another model rolls out, but there isn't a lot happening there anymore. So difficult to set it up in practice with a couple of these things that we have discussed. Yeah, this leaves us at a good ending point for next week.